wait a little bit for... Olha, mas ele vai fazer sozinho?
Do you have some paper to lay underneath my mouse?
Yes, I have one.
Because the mouse laser doesn't interact well with the
with like
the
Yes.
glass.
Here. Thank you. Here.
Yeah, much better. Is there a toilet here? Or is that
The toilet.
the toilet?
tourists, I think, left.
Okay.
Yes, I think my
Yeah.
Yeah, it's really cool.
Yeah,
Mr. Song.
Luigi.
Are there still people coming, or?
I had some hard time finding the room through this alternative route, but I think, I don't know,
Yeah.
I can see more.
I don't think there's more people.
Okay. Then we can start. So, I'm not sure whether, so we are going to do a hands-on session now about change detection using SAW data. And so I'm not sure whether all of you have the data. I think it has been handed around on Tuesday already, and should also be available in the Dataverse, but I'm not entirely sure.
Can you show us exactly what they're referring to? Is it the one that's called Hidalgo change something?
Yes. So there's a
There's a bunch of files, everything Hidalgo or something. In the Julia use case for change detection folder.
there should be this. There should be one ZAR file, so one folder with a .zar ending, and then some of these shape files. And yeah. Now I have to find my mouse again. So if anyone is missing the data, we can also, we have a USB stick here. We could share it around. Yes?
So in the folder called Julia use case for change detection, there's a bunch of the data files, but where's the notebook?
Yeah, we're coming to that.
Okay, so
The notebook is on the, so I have a starter notebook. I just made a pull request to the JuliaEO package, so it should be on GitHub. In the hands-on sessions, Julia use case for change detection. There's the use qa.ipynb. And we're going to start from here, and then we're going to do some live coding. Now I first want to give a short introduction into what we're trying to do in the next 1.5 hours or so. So we want to look into using recurrence quantification analysis for change detection in Sentinel-1 data. So it's a use case of deforestation analysis on a why is that not working? On a small area in Mexico, and we're using recurrence quantification analysis, which is a nonlinear time series analysis technique. I'm going into detail what it is exactly later on, but mostly the aim is to get a feel for working with SAR data and also working with the data sets in Julia. So first we can have a look into our area of interest. So I actually started to sort of thinking we might be able to do also a case in Yucatan, but we're going to focus on this area here on the left. So it's in central Mexico, and there are some deforested areas which we have detected manually from high resolution optical data, and now we want to see whether we can actually map that in a automatic way from the Sentinel-1 data. And so is everybody set up with a notebook and the data? Was there people still struggling with that?
I'm still trolling it.
Then
Felix, just curious question, like this task of trying to predict deforestation from Sentinel, right? Like,
yeah.
Is it intuitive to do this? Like, I'm asking as someone that's not like used to the type of data that, right? Like, is it like a depth information? Is it like color information? What Sentinel holds that would be related to deforestation?
So the what we use here is that as I showed on Tuesday, you have these different scattering mechanisms, and I just show you the presentation again.
Yeah, I remember like your presentation.
But makes it easier to just look at it again. We have these different scattering processes.
Yes.
And what we actually using here is the differences between scattering process A, where you have a rough surface, something, and where a lot of the things are just scattered away to somewhere. And then
versus
either D or E,
yeah,
where you have either interaction on top of the canopy,
yes,
which is a different roughness, and therefore has a different scattering mechanism, or you can have a this volume scattering where you have more interactions inside of the canopy, therefore a higher scattering back to the sensor.
Okay.
And that's the rough idea of why why SAR should be able to see that.
Right.
At least for the methods that we're using. There are also approaches by which you try to use the difference between D and B, for example, but that's not something we're going to do.
Thanks for the illustration, really clarifies things.
And yeah, I actually wanted to just show you the data real quick, but somehow my plotting functions are not working, and that's the danger of live coding. So now you're stuck with me here, so you have to help me debug this. Actually, I'm just going to do. I'm just going to lower this so that's much to. Wait. What? No. What did I do with the share screen, and why can't I do go back?
You have to share your screen.
Yeah, but I'm just blind. Okay, yes.
Yes.
There's a green button I can't see.
Yes.
Okay, yeah.
It's okay.
So in these files you downloaded from the GitHub, there was the notebook in which we're going to just work, and then there was also this helper function, and I actually tried to. Yes. So anybody still struggling, or it's all good? Okay. So the first thing I would like to do with you is to actually look into the data. So if you would like to play around with it yourself, you have to change on line 160 to 162 in this plot Sentinel-1 script. There was an S1 VH here, and this should be S1 Paul for all 3 lines. And then it hopefully just works. So what you see here is, okay, the projector is not good enough that you can actually see that, but what you see here is the Sentinel-1 data. On the left, it's just 3 different time steps from different times of the year. So it should be roughly fall, summer, and autumn. And on the right, it's the temporal statistics of 25 quantile, median, and 75 quantile. And so we could also just change it here. And then what you could see, what you should be able to see if the projector wasn't as bad, is that you have this darker spot in the middle. This is mostly agricultural area. Here there's an even darker spot which is a lake, and then you see these brighter things, and then you also on the edges you see these deformations. These are the geometric distortions I talked about on Tuesday. These are the layovers, shadows, and so on, which have been so strong that they couldn't have been corrected. And now we can zoom in a bit on a area that is a bit where I know that there was a deforestation during the time frame of this data set, and you can see the slight difference. So in the RGB, you don't see that much, but you can also squint a bit and see a bit a small pattern here and a small triangular pattern here of slightly different noise, I would say. And on the right, on multi-temporal statistics, you see a bit of that, a bit clearer, and this is the effect that we are actually trying to look for. And so in the notebook, we should just I'm just going to go out of this presentation mode. So we loaded the packages. Then we can just load the Sentinel-1 data. Then I apparently changed stuff. Okay. Did I might have so you should try to copy your you should copy the data that you had on the drive into the folder here. So I'm assuming that we just have a data folder here, and then we just.
Is it okay just to change the path, right?
You can also just change the path if it's whatever is easier for you. I mean, your computer, your choice. Okay, but I just copied it there. Data.
But then that was small chunks. Didn't I mean that implemented stuff.
So finally, I don't know what I spelled wrong there. So we loaded the data. So here you see that the data is has a longitude, latitude axis, has 104 time steps, and has 2 polarizations. So we have VH and VV, and now we can convert the whole thing to dB. So we can do S1db is map of S1 cube. The other way around, of course. So we do first. Never should have given that a name. And I should have included this. So I'm just loading the helper functions. So I wrote a few functions for the DB, for this plotting, if you would like to try this out and explore the data a bit more, and also for masking data later on. Now this is included, now this should work. And this is also just as a side mark. I'm going to go into more detail tomorrow, but in the JuliaEO hands-on, this map is a lazy operation. It's not going to do anything. It's just going to register. If I'm going to access data from S1db, I'm going to apply the db function again on S1 cube data. Now we also need to let's get rid of that. We don't. That's also in these helper functions. So now we want to just load the data that is in the forested and deforested areas, just to compare the time series. So we have these. So basically, it's based on the. Where's that coming from? Oh, yes. So we had a so this is just a broken mask cube. So this is just based on the data from high resolution data. On the polygons from high resolution data. And so this mask cube function is a function that just takes a data cube and a polygon, a shapefile, and just extracts the data which is underneath every polygon inside the shapefile handle. And so we get a data set back that is basically has a data cube for every polygon. So in these, for example, these are 80 pixels that are inside a forested area. And now we're going to just continue to work with this one data cube. And now we first want to have a small look into the data. That is taking some time. And here we just see, I mean, this is just There's something going on. This doesn't seem right. This should be 80 lines of things. Okay.
Look at the animation.
Is it working for you so far? Or?
No.
I had some package issues.
Ah, okay.
Yeah.
Great.
Why X-ray base is not found anywhere?
But I think
Yes.
it's also, I think it's from the manifest. It's trying to do like my error come up with like development, Felix Kremer,
Oh.
not found.
Yeah,
thing.
yeah,
So
yeah, yeah.
Cube not defined.
Yes.
Right, we had a let me just.
But is there a reason like why to use the development version? Does it work?
No,
with
no,
that?
there's
Okay.
actually no reason. It should. Not a good one at least.
Okay.
Just create, and then that's also what I just did. And also in the yeah, I think I missed a step. I missed to tell you a step in the beginning. I made it somewhere. Are you working on your own machines, or are you on your own systems, or are you working on Docker?
Own system.
Own system.
So let me phrase this differently. Who's working on their own system? Okay, and who's working on Docker? Okay, and in Docker it works, or?
No, have packages problems also with PTG.
Okay, I think for that you should just, I mean, try it. Can you do inside of your inside of Jupyter you can do a closed square bracket, and then you should do. I thought that I had that somewhere, but apparently that I didn't. So you can just install all of the packages I used so far. So basically instead of, so copy the cell,
Okay.
and then replace this using by the closed square bracket followed by add. This should add all of the packages into your into the Docker system, and then you should do the same for these other packages a little bit below. And on your local, you're running into issues because I put some def into the project terminal.
Yeah, I fixed that now. It says cube not defined.
Then you should just did you do using Yaxarrays?
Yeah. X-ray base.
All of this Jackson race.
Yaxarrays
Okay, yeah.
Let's try
with an S.
race.
With an S, yes.
Let's try and add it.
So skip one.
Okay, let's see. Yeah. I had to delete all the stuff from your project, Tom.
Yeah, that might be, yeah. Yeah, you don't actually need. I mean, you could do.
Plot.
Yeah, if you want to do plot, then you have to do JuliaEO. So, did this work by now? What? Just do it again. Yes. Fix that. So you can continue to work on JuliaEO if you want. But I have to. I currently have to work on Kairomaki because I run into a JuliaEO bug that doesn't let me print lines. Okay. There's still something. There's still a bug in here somewhere that should have been fixed. This should actually be multiple lines, but actually you can still see the point I wanted to make, which is that in the forested area you have some noise, but basically everything is just staying on the same line, roughly in the same area. And now we can do the same for the deforested areas, and just plot that as well. And now that is also not working. Wait. Yeah, this is some selection bug. I'm just going to show you shortly what it actually should look like. What we should actually be seeing. So on the left you have the deforested areas, on the right you have the stable forest areas, and you see this. So this is just a selection of 25 points, and the colored lines are the averages, and you have a drop here in the backscatter. Why? Because of the deforestation event. And so the question is how to capture this. And one idea is, or what's proposed is that you can just use the difference between the 95th and the 5th percentile. So you can just say, okay, I'm just going to put a threshold here and the threshold there, do the differences, and then I will get some higher differences on the deforested areas compared to the forested areas. And this is what we are just going to compute. So we're going to do using statistics to load the statistics package. Then we can so unfortunately we can't do the computation of the percentiles for the forested and non-forested areas because our selection is currently broken, or at least my selection. Maybe it's working for you, I don't know. So now we can define this quantile function. So we're going to compute some quantiles. This is just the output. We're going to put the data in. This is the input, and this is the threshold. So in our case, it would be 0.05. And here we just have to make sure that there are no missing and no null values inside of our time series. And
Question.
What?
Is your, since we also have to write this function, we also have your full notebook over there, are ours different from yours? Because I don't have the same on the same lines as you.
This one?
Like, no, on this one, the right to the right, yeah. I don't have the same function on line
Okay.
67, let's say.
Okay. What's different?
Like on line 67, if we're just loading the cubes, forest cubes, data ticks and stuff. I'm just put.
But you find the same lines there, right?
You just updated the code before the session.
Okay,
I think I just.
great. No, I found it on line 100.
Okay. It might be that I just during the session deleted stuff on top. I don't know.
Yeah.
Sorry for that. And then we're just updating the output by computing the quantiles of the time series for basically the threshold on both sides of the end. And now we can define an output axis. So this is because we're going to use the we're going to use the map cube functionality from Yaxarate, and here we're just going to do. How do I get a new? And now we can do a Q5 cube.
It's not supposed to be. I think it's like a mess.
We compute the map cube from quant S1 dB 0.05. So this is like quant is the function we want to apply. S1 dB is the data we want to apply it on. This 0.05 is the threshold that we are going to put in our function. And then we also have to define the input dimensions. That's a bit also what Fabian talked about earlier, right? And as outdims, we can just use this out axis we just defined. And of course, I forgot something. What? No, that should be working. There's some difference apparently. Right. Oh, I forgot something, yes. As I said, you have to wrap it in an outdims type. So basically by this you're telling the map cube function which are your input dimensions and which are your output dimensions. And so now we can also just define, defining some helper functions for plotting, so that we don't need to write this and think about this all the time. So this is just going to use the plot map. So it's just going to use a heat map and using the longitude, latitude information from the cube as a plotting, and then we can just do plot map of Q5. Are you following along so far, or?
Kind of.
No?
I think there's always like I always need to install one more package.
I'm going to go around in a few minutes. We're just going to plot one last thing for these percentiles. Because now we plotted the percentiles of the lower bound and now we can also plot the so we can see that in the high bound, so in the upper value we have not much distinction between the forested areas and the non-forested areas, which we also saw earlier in the time series plot, because the upper bound was basically quite similar. But if we use the low bound, then we can see a few differences, which I unfortunately currently can't zoom into. But you see some patterns here, and basically we can now also just use the and now we can just use the we can compute the computational the range and just say, okay, what is the differences? What is the difference between the higher and the lower values? And now we can do plot map of p range. And yeah, okay, so it's not the signal is not very strong and the projector is not helping. So I'd say I'm going to go. Wait, no, we just do one last step, which is we can also I selected an area that would be a bit more interesting because there's something happening actually, so we can just define these zoomed windows, and then we can do Q5 zoom equals Q5 Q on Q1 that equals zoom that. Did anyone? Plot map of Q5 zoom. And here we see a bit more of there's a pattern here, and there's a few patterns here, and we can also do p zoom equals count range of Q5Q, not Q5Q, Q5 zoom. And now we can zoom into here. We can plot map this. And now we see that these patterns are emerging, and so we're not going to do it today, I think. But if you would look at the shapefiles that we detected from high resolution data, or if you would compare this to high resolution data, you see that in this case there's a deforestation in 1 year on this triangle, and then there was another deforestation a year earlier or a year later on this other thing. That's also why we have a bit less clear image here, and there's similar things happening in this larger spot. And yeah, I think now I'm going to walk around a bit, see that everyone catches up, and if you are this far, you can also have a look into what happens at the other polarization. So now we plotted out everything for VH. You can also could have a look into what's in VV. Yes.
I have a question. It's why the range increases in the VH? Like we're doing the quantiles over time, right? So why is this happening when the forest is removed? You know that?
Because the VH value is dropping.
Yeah.
That's why the range is increasing.
Okay.
Like you have standing forest here.
Yeah.
For a year.
Yeah.
And then you have a quite high. That's all.
Yeah. Okay.
We have a high backscatter or high-ish backscatter, and then the forest is removed.
Yeah.
Then the backscatter value also drops because you have less volume scattering.
So we're doing the quantiles over the time range where there's both forest.
There was first forest and then there's no forest, and that's also why you saw the differences in if you go up here, right?
Okay.
In the Q. I didn't show this soon apparently. Yeah, here you see it in the low bound. You see a bit.
Yeah.
But if you would now change this to the high bound, I would expect to see mostly noise. I mean, you can't see. So it's actually so the range is increasing because you have a drop.
Okay.
And I think why it works a bit better with p-range because you're basically removing the random fluctuations of this is always a bit higher or this is always a bit lower.
Yeah.
From your spatial structure. Yeah. So are there any other questions or issues that we should try to solve about bets? It's looking good.
Yeah.
And then you could have a look into the VV data.
But it already computed.
Is it working or you're lost completely or?
No, I was not the data set.
Ah, okay. Would you like to have it?
Yes, now yes.
Yeah.
I have it.
You have it? You have it now?
I have it now. I found.
Ah, okay.
I found
Should have.
Sorry, no.
It's okay. That's fine. You're trying to. I just want to help everyone who's trying to follow along. Is it? Did you try it? Or?
Yeah, I'm trying, but just a matter of computer power. So.
Yeah. And you can. Do you have a multicore?
Yes.
Then you could try to add these using distributed using, and then
Yeah.
this add workers,
Okay.
add procs, then it should do.
It's a Visual Studio that is
Ah, okay, yeah. Okay.
Trying to read something.
That's also fine.
The
That's-
documentation, yeah.
Yeah. You have to start somewhere.
Yeah, I have to understand more the basic concepts about it. But yeah, it's very interesting.
It looks like a lot.
Yeah,
I was.
I did the packages that you said, then I got to the cube and give me a lot of errors. I tried to find a path for my
Thanks meget for
There's
en
some-
BB over
there's just one. There's- for some
over
reason
den,
it's
der er lidt
not-
i kanterne, ikke? Ja. Jeg skriver
Yeah, you use.
Så det er jo egentlig mere at se, at det er et eller andet, der er en eller anden stærk skatter her, som er et eller andet.
X.
Jeg ved ikke, hvad det er.
Men ser det, hvad så står der i V? V? Nå, du ser V.
Ja.
Okay, ja, det kan vi. Ja.
You're inside the Docker at the moment.
Yeah.
Then we can do that.
You having the same, similar thing? It's just
Ikke, man kunne bruge den her flot
seems that you have
Jeg har ikke prøvet at bruge den.
Det er sådan en klub.
Nej. Jeg tror ikke, jeg tror det er en klub. Jeg bør ikke have refereret til det.
Som ser flot ud.
need to read this file name, right?
Nej, men jeg tror også, jeg missede lidt, hvad hedder det, den del af det.
Det er så dårligt til at bare stoppe.
It should be working with the local path.
Det er et godt
With the
spørgsmål.
right path.
Hvis jeg ikke tror fuldt, hvad der sker.
Jeg tror ikke,
hvad
det
der
er
sker. Jeg kan slette den her. Hvad der sker i billedet kører. Er det ikke det langt?
Yeah, I had similar problems earlier that somehow.
Det er jeg ikke sikker på. Måske.
Nej, altså.
Jo. Altså, lidt, tror jeg. Men det kan jo være, fordi det egentlig er sådan fejligt. Altså,
Man kan ikke kalde det. Så spørgsmålet er, det kan man bruge til at tage med.
nå, du kan godt stoppe nu. Du kan godt finde nu på den næste. Er det? Du kan trykke op den der slår.
Nej, det er jo det, jeg vil gøre.
Den er så tryk interrupt.
Why?
Nej, det er din. Det har jeg ikke.
Okay. Altså, det kan jeg gøre, hvis det tager med, så skal du komme ind på.
Det kan man ikke gå.
Ja.
Hvorfor kan man? Nå,
Det er
det ligesom kontrol C.
Ja.
We are in.
Det er 100 billeder, hvis oven på hinanden.
Funktionelt til at bruge for det, så fungerer det.
So we can try to delete everything from here. Because I think
Ja, 104.
that looks good.
Billeder.
Without the, I think it's just a strange thing that inside of Jupyter, the path is not really clear whether, yeah, now it's loading. I think it's more Jupyter thing that you have a path there and you have and it's I don't understand this. It's,
That's the political argument.
No, but I'm working on my
Så sidder de her på deres egen computer.
there's
Mere
something
i fysikken forstår altså, det er mange der til at fungere på dig.
yeah, just delete
slightly on the notation.
Delete everything? No, you can closing square bracket. Just delete everything. Closing square bracket, and then free Yax arrays. Free. The problem is that I was not that good of me. I added a local dev path into the manifest, and that made some errors.
Okay.
You're good, right?
Yeah, I'm not just following because of the hardware. I don't have enough hardware
Okay.
for everything.
Ah, yeah, okay.
It's just a tablet.
Okay, now it's roughly running for everyone, or now we can have a look into the other into another method, which would be the recurrence quantification analysis. So recurrence quantification analysis is a nonlinear tool. So the idea is that you compare the time series against itself, and based on some threshold, you say, okay, this time point is similar to this other time point, and then you get so-called recurrence. Recurrence matrices. So loaded now. We can have a. So I'm just showing this on an exemplary random function. So we have this. Does anybody know how I can make Jupyter Notebook to make a new cell if I run one?
Control A or B if you want it above or below.
Yeah, but can I just if I run the one, that it just automatically makes a new one underneath? Does it work?
If you execute it, the result will give you.
I think you just trying to say like you execute the cell and create the next one. I think it's control enter, right, or something, or shift.
Yeah.
Execute the next one.
Okay.
Just controlled by right side.
It's right and creating a new one.
Control Shift Enter. Doesn't work.
Oh,
Shift.
sorry, Shift Enter.
Shift Enter. Ah, yeah, that works. So what happened now? I don't know. Okay, I forgot to load the distributions package. And, yes. So now we have a random. So we can do lines of TS step. And now you see this is just a random example to understand this recurrence analysis a bit better. It's just it's a bit similar to what we're actually seeing in the SAR data. You have some random deviations, then you have a drop, then you have another random deviation. And you could play around a bit more, changing the standard deviations of different parts of that, also, and so on. But for now, I think it's enough to understand the concept. So now we can do. We can compute a recurrence matrix based on this TS step, and this also needs some threshold, so we can just randomly select one. And now we can do a heat map of this thing to be great. Now we just can we just plot the recurrence the recurrence matrix of this. So this is just comparing every pixel against every other pixel and saying, okay, they are similar if the difference is smaller than 2. And actually it's going from, so it's, I don't know why, but it's going from the right bottom to the top left. And so you have always the similarity of every point against itself. And then you have these large blocks of, okay, this is similar, like in this area every time step is similar to every other time step, roughly every other time step. And this corresponds to this area here, or this time frame here, where you would have a lot of similarity because the difference is, because the standard deviation here is 1, I think. And then you have this, then you have these parts here which compare the higher random noise against the lower random noise, and then you would, so therefore there's not much similarity, and then you have a high similarity again on the lower part of the signal. And what we can do now, well, what's the next step is to, I mean, that these are nice to look at, but you can't do that for every pixel, or you can't look at them for every pixel. So you can compute different statistics out of them. So, for example, the so-called recurrence rate, which is just the amount of similar pixels was black dots in this recurrence matrix, and this tells you a bit about how much similarity is there in your time series. So if it would be 1, it would all be the same, and if it would be 0, then there would be no similarity between any point in your time series. And this of course this recurrence matrix, and therefore also the recurrence rate, depend on the threshold you set to define similarity. And to see this, we can use the we can just compute the similarities for multiple of these. So we compute the recurrence matrix for the same time series but for different thresholds, and then we compute the recurrence rate. And now you can see basically there's for the recurrence rate there's this it's just filling up. I mean, it's just that at some point it reaches 1, because then every pixel is similar to every other pixel, or every time step is similar to every other pixel. And the other metric that is much more interesting for us in the edge detection use case is the so-called recurrence quantification trend. So it's basically the correlation between the, so we are calling this diagonal that's going from lower right to top left, the main diagonal. This is basically the comparison of every pixel, every time step against itself. And then you have the other diagonals, which are basically comparing pixels on a fixed width. So it's just every 30 days. So what's the difference between pixels in a 30-day rate? And so the trend is the correlation between the pixels on the diagonals and the distance of the diagonals to the main diagonal. So it's basically how much depends the similarity of pixels on the time that has passed away between these time steps. And so we can now compute the trend of this. So it's most often a negative correlation, because the similarities are decreasing, and now we can do a very similar thing to just compute the recurrence trends on this. So we and here we have a U shape, so it's basically just saying in the beginning all pixels are different. If your threshold is 0, only every time step is similar to the other time step. And then your RQA, so then your trend matrix is decreasing, which is basically having more information, because there's a difference between the pixels that are near the main diagonal and the pixels that are far away. And then as you increase the threshold, there are more and more pixels that are going to be equal. And then you can't distinguish anymore between pixels that are far apart in time and pixels that are nearer together in time. And we could try to, we have 20 minutes left, right? Roughly.
Yes,
So I actually thought about letting you play around a bit with these different things. So maybe you can do it later, but because this, as you could imagine, this also depends on the noise levels and the differences between your different parts of the signal. So we can now basically do the same, do what we did for the percentiles, for the RQA trend. So we're going to write a few we're going to write a function that applies that's computing this RQA trend on every pixel, and apply this on the Yes.
I have a question here. So right now you're computing this trend, but if you have like a side image where you have like a homogeneous area, and then you expect it to change to like another homogeneous thing, would it be like possible to work some of these things out analytically and like actually be like to have a constant fall alarm, or to have the optimal detection of the change between these two? We would have to place it, because I think the distributions of the noise in the side image is quite well known.
Good question.
Yeah, it's just if you know someone who. Okay.
I mean, actually, you're reminding me that I should definitely show you this. So, because now I showed you the recurrence matrix for this example, but this is now the recurrence matrix for actual deforestation and non-deforested areas. So now it's a bit different. Now we start from the top left, from the bottom left to the top right, and this is not it's not a real recurrence matrix, but it's the overlay of 25. So we have these 25 pixels that make up this gray area at the mean, and below basically every it's just the sum of these. So the totally black points are similar in every pixel, and the lighter it gets, the less pixel you have that are as expected as similar. And you see that we have a quite similar pattern to this random noise thing we looked at earlier. On the deforested areas, and then on the forested areas we don't see anything. It's just random noise, because everything is basically randomly similar or not similar. And this also depends a bit on the threshold, and you also see these things here. These small patterns of, okay, there's something similar to the signal previously. This is basically this peak here. That suddenly for a few time steps, it's just similar to whatever happened before. But now I think the really interesting thing is to look at what does this look like in
So this way of looking at the data, it also makes it a little bit easier to extract the time point of the deforestation compared to the ranges, right?
Yes, it should. I haven't looked into that yet,
Okay.
but that could be an interesting follow-up to
Yeah.
see whether you can find the actual time of the deforestation. Because what we saw, let us just plot this,
Yeah.
and then I'm going to show you these differences. So we're going to use the trend, we're going to use dB, we set a threshold of 3, the index is so here we just apply this trend function on our Sentinel-1 dB cube. Then we set a threshold of 3. We need as input the time dimension, and the outdims is empty because we are reducing the whole time series to one value. And this is taking some time for some reason. Simon, I think while we wait for the computation to finish, I can show you what I mean with these. What gives an indication of whether it could be could be possible to detect the actual time of the deforestation is when we looked at the so the orange ones are deforestations that happened between 2017 and 2018, and the blue-purple polygons are deforestations that happened a year earlier. And you can see the RQA trend on the left and the percentiles on the right. And you see on some, on the VH original, you see that in the RQA trend, you don't see much of you see bit differences between the earlier deforestation and the stable forest. But in the percentiles, you see a lot of quite similar values in the previous deforestations and the actual deforestation. Because what happens is that the Sentinel-1 time series of the deforested areas is moving from high noisy values for the forest to some seasonality that also reaches the value top of the high bound of the forest that was previous there. And therefore if you then use the percentile range, it's quite similar because you just reach the top a few times of the year, or one time of the year for a few months, for a few weeks or so. And therefore you can't as easily distinguish between the deforestation of this year from the deforestation of last year. What? now we do the taking too long, so we're just using Yax arrays. So we're, I didn't want to wait 10 minutes for the computation to end. So I'm going to use distributed processing to speed this up a bit. So I'm using distributed, then I can add multiple processes. Then I have to use PKG to activate the project I'm in, because otherwise it's going to complain that it doesn't know where stuff is, and then I have to do using Yax arrays. And now I have to make sure that the inner function that I wanted to compute is available and on every worker. And for that to work, I also need to do load the recurrence matrix, and now we can do this computation again, and it should be faster, hopefully. Okay. Of course, I forgot anything, something. Maybe it would have been faster to just wait. But okay, in the meantime, are there any questions? Okay.
question. Julia?
Hmm?
Did you see something like that?
As a packet, wow, I've never seen this.
Can you do a...
Maybe
Can
you
you
want
go
to
in?
see a folder which is
Can you just do... How do you close brackets? Square bracket? Or do ST?
Okay, so we have lunch until 1 o'clock, and then we all meet in the main room, and then we go to the...
Okay.
Thank you.
Yes.
Wait, let me. So we're closing the session now? Or are there any questions from the online participants?
está a gravar no Zoom. Já está em direto. Mas não está a gravar no Zoom, pá. Ok.
Espera aí, você. Vamos gravar.
Ja, det er fordi det her, det er sådan en skibsretter, det er deres redningsskib. Det her, det er selve, det er pige. Men det er i hvert fald sådan noget, man selv vil, hvis det er sådan noget,
Okay, welcome to the session 2.2. For those who are following us online, sorry for this little delay, but we need to come up to the other room. So this session, it's about machine learning with geospatial data, what can go wrong. And we'll have Dr. JuliaEO that has more than 10 years of experience in advanced statistical theories for geosciences. He's the creator and lead developer of the Geostats JL project, as well as various other open source projects that are widely used by geoscientists around the world. Okay, thank you.
Thank you. So hi everyone, let's start another session here. So what my plan is in this talk is basically like raise some of the issues that you may encounter when you're training learning models of geospatial data and why they happen, right? So the plan is to switch between like, a couple of slides just to illustrate what these issues are. Then I will try to switch back to that second notebook we didn't have a chance to cover in the hands-on and just skim through some examples with actual code. So if you actually want to reproduce part of the presentation in your machine, doesn't need to be now. The same notebooks we shared on Monday, they are already available on the JuliaEO 2023 GitHub repo, and you can follow with your own time later, right? So, first question here, which is the question that happens all the time when you're doing machine learning, right? So, I don't know if that has ever happened to you, but it's like pretty common if you're doing machine learning with geospatial stuff, which is the following recipe here, right? So you train your models using samples from a source domain. I'm calling here this domain in blue.
I need a minute.
Yeah.
Yes, you have to join the Zoom session and share your screen
Oh.
on the Zoom session. Is that possible?
Yeah. I don't know. I don't know how that's done, but let's get the link on the Gmail, right?
Yeah, we're sending emails.
Yeah. Let's see.
Sorry.
JuliaEO, I think I have a
But then you need to give him access to share it because he's just a participant, I think.
No, we got a link as
session, I guess.
I hope that works. We'll see in an hour.
Yeah, but it might be necessary to get ready to authorize the
So that's
screen
the.
share.
So what's the link I should
It should be down there.
Oh, you're in the session.
Parallel session.
Join webinar.
Join webinar.
Yes, overload the presentation a bit more. Okay.
This meeting is being recorded.
So what do I need to do extra? Should I move something?
Share screen.
And then entire screen, right?
Your presentation.
Okay.
Perfect.
Okay. Okay, so coming back to the presentation, what do I need to do to let me just
Mute.
yeah. Maybe not. Let's see. I'm still hearing like reverb.
Yeah, you need to cut the sound.
I turn off the sound.
out.
Oh, the sound itself. Here. Got it.
All sound.
Good. Coming back. So what happens here, right? So you have a geospatial domain where I'm splitting part of this domain into what I call source, D sub S for source, and another domain, D sub T for target. We will be training models in the source and trying to make predictions in the target, right? So you start with your workflow, you train your models in the source domain, and then you try to estimate which model is best, right? So you have a list of models, decision tree, logistic regression, whatever this model is. And the ways that we usually, let's say, rank models is by cross-validation because you don't have access to labels in the target. So you take a cross-validation procedure in the blue area, And then you say, okay, according to cross-validation, my best model is model 1, whatever, model 2. You create this selection, right? You rank the models, and then you apply the model in the target, D sub T, and then you realize that there's a big surprise. Like you say, okay, my model performance is actually quite poor in the target, and the actual error is actually it's prohibitively high. And so why this happened? Like this happens all the time, and I reviewed like one paper recently that the same thing occurs, and every time I review a paper of machine learning in geospatial stuff, the authors rank models and they pick the one in the top, which is actually not the best model. And the reason for that is kind of understood. So this slide is a bit abstract, but I'll try to go over this illustration here so that you get the big picture. The intention here is not to go into the exact understanding of things, but just get an idea of what's going on. Imagine that I have like two images, Z1 and Z2, which are my covariates. So these are the variables that I'm using to train a model, right? So any image that you can imagine or something like this. I'm creating here this plot of circles, this standard, let's say Gaussian, right? Everything is like just perfect. And then you see that this space gets deformed as you increase the spatial correlation, right? So you go from perfect circles to something that's completely like, it looks like what we call a manifold. And the problem with that is that like sometimes you're training in an area, because real world has spatial correlation, right? So you're training in an area that has like a shape like this, like a moon or a banana like this. And then when you apply your model, the banana is like this. Like you're from one region where the distribution has like some manifold, and then you go to another region where the model has not learned anything here, right? So you learn a bunch of relationships in this area, but when you go to the target domain, your banana is, let's say, flipped to some other distribution, and you completely lose the performance of the model. So this has to do with the fact that traditional models and methodologies developed for machine learning assume that your samples are IID, right? Like identically equally distributed, right? But when the samples have spatial correlation, which is the synthetic example here, you lose a lot of the properties of the models, right? So that's one reason why things fail. The second reason is shifts in distribution, right? So the first one is like just the fact that you have spatial correlation, you create these deformations in the feature space and you lose your performance in the target. The second is that like usually like in physical world, you have trends, right? So you have a physical process that, let's say, sediment deposition, or there is a trend of like a cold front moving from left to right. And so you have areas with higher values of some covariate and areas with lower values or something like this. And if you train your model here, and if you think of the covariate distribution here to have some given distribution here, but if you go to another domain, it will be shift to the right, for example. And this is called data set shift or concept shift or whatever shift there is. There are many names for the same thing, but it's basically saying that the source and target distributions, they don't match. And because of that, again, you are training something in distribution A, and when you want to make performance predictions, you go to distribution B, and things just don't work anymore. So I'll try to switch to the notebook to show, let's see if it works here. Some of these things live, right? So this notebook, let me share the full screen. Share the screen one, I guess. And if you go to, let me stop the presentation. Yeah, so if you go to this notebook, which is the one that we already have access in the hands-on session of Monday, you can follow some of the steps here to see these issues actually happening, right? So the first example here is the example I just showed in the slide. Let's see if the visualization is gonna load here. I should have loaded this before, yeah. So you see these are the same example I showed in the slide. So this is an actual Mackie visualization. I should be able to zoom in and zoom out, but I don't know if it's responding. My tablet's not very responsive. But so you have a source region here. Oops, too much. You have a source region here where it's just like have a collection. Man, Mackie. You have a collection of pixels. Let's just reset the thing. You have a collection of pixels with labels, which are these blue ones, and you have a collection of pixels that we want to make predictions, right? So if you do this, just ignore this error warning here. If you do this procedure with cross-validation, what happens? You get this source domain, you break it down into smaller subdomains, 1, 2, 3, 4 in this illustration. You hide one of them, you train the model, and then you predict the error in the one you've hidden, right? So everything is concerned with your source domain. The target is completely outside of revision at this time, and then you just estimate this error of the model age as this average of errors at each of these subblocks here, right? So you say, for the jth subdomain of the source, I estimate some sort of error, which is based on this loss function. So you take a loss function over the prediction of the model and compare that with the actual label you have on that domain, and you create this estimation of error fully based on your source. And then what happens is, if you go down here and you look at the actual result, you see that the predictions in the left, let's see if I can zoom here. I'm always against the correct direction, so let's go here. So if you zoom here very closely, you see that many predictions were like incorrect just because the model was not aware of the geospatial location of the samples, right? So you have yellows inside of the black and all this mixed up prediction just because this is the actual label, right? Just because the model has explicit saying about like where the coordinates are, right? And if you see the error that you estimated with cross-validation is about 2 times higher than the actual error that was expected, right? So the error that you get when you apply the model in the target is 2 times higher than the error that you estimated with cross-validation. So that's very dangerous for deploying models in the real world, because you think your model is good, then you change the area to some other area, just screw it up.
Julia?
Yep.
Can I make a question?
Yep.
Did you take the coordinates into the model?
No, just the covariates, just the covariates, yeah. And so the explanation, again, let me just take the guy out here, yeah. The explanation, again, is similar to that illustration I showed before, but the cross-validation procedure, the naive one you have in scikit-learn and all these frameworks for doing machine learning, they are random splits of the data set, right? So you get your domain, and you randomly select samples to be in fold 1, fold 2, fold 3, fold 4. And by randomly selecting folds like this, you get in this situation where fold orange, fold red, fold green, and fold yellow, they are spread everywhere, because this is a random sampling. And because of that, when you hide fold red to use as your hidden fold, and you train the model with the rest, we will always have a sample that's too close to fold red. And because they're too close and there is spatial correlation, you'll be kind of leaking information to red, and you have over-optimistic error assessment, right? So that's what is causing that expected error to be like much lower than it should actually be. So there are alternative methods for that, like in the literature. So it's pretty much this umbrella of geostatistics, right? So you have other methods in the literature that try to create estimations of error that are more conservative. For example, block cross-validation. You take your source domain and you split it into these blocks. And the idea here is that you're going to hide one of these blocks, and you create this thing called the dead zone, where you cannot use samples from here in your training. You train with everything outside, and you predict in the red. So that's just a virtual, let's say, way of removing the correlation length R that you specify a priori from your estimates of error, right? So you repeat this process block by block until you get an estimation of the error. And here's the equivalent of leave one out, right? So instead of just hiding one sample to make the error estimate, you hide the sample and you also hide a radius R around the sample, and you repeat that. And so the good news is that these are very tricky to implement for arbitrary geospatial domains, but geostats.jl has all these implementations in parallel, so if you need to do this kind of stuff, it's already there, right? So that's the code you actually need to execute to get these estimates. So up there you see there's a classification task where I'm saying I want to make predictions of the crop type based on 4 bands of the satellite. So there's a table, this is a table with 4 bands, and the target is the crop. It could be a raster image or it could be anything, but you're just defining the task that you want to perform. You define your learning problem. In this case, it's going to be this geospatial learning problem where you have the source domain. I've been calling D sub S here, but it's omega sub S in the code. You have the target domain, and you have the task. So this encapsulates all the information you need to perform the training and prediction, right? After that, you can load any learning model from the MLJ stack, which is the Julia stack to load basic models from, let's say, all scikit-learn models are currently supported, plus other models implemented in Julia directly. So you have more than, I don't know the last number, I think 108 models. It's like a huge number of models. And here I'm loading the decision tree. And after you load the decision tree, you can wrap it up into this strategy here that I'm calling point-wise learn, which basically says, okay, that's going to be the naive way of applying the model. You just go pixel by pixel making predictions, or pull all these pixels into a big table and make the prediction. But there are possible alternative ways to do that. Here you're choosing the misclassification loss as your estimation loss, right? And then you create the procedure, which is block validation. We changed name in the latest release, but you can find that in the documentation, where you specify the radius R that I illustrated in the illustration, and you specify the kind of loss for the target variables, right? I'm saying, okay, for the crop variable, I want to estimate error with misclassification, because it's a misclassification problem. Then you can call this function error of the learning strategy on the problem with this method, and it will return a dictionary with all the errors for the targets, and I'm just taking the result for the variable crop. And here is what you actually have in terms of predictions, right? So if you actually do the naive error estimate, you'll see like the actual error estimate, which is the actual error you get. Like you see that these two values here are much closer now, 0.23% misclassification, because you are using this radius 30 to avoid that over-optimistic error estimation, right? Another reason why we think it's important to start embracing this idea of doing geostatistical learning and not machine learning with geospatial data is that you have ways of designing new models and new algorithms that are more adequate for geospatial data, right? So you're not just taking a toolbox that was designed for tables, applying to geospatial and pretending it will work. You actually start to think actively about how to actually develop new models for geospatial data. So here's another example where you have an image and you want, for example, to segment this image into subdomains, for example, right? And that's usually an important step in modeling, because nature is super complicated. You want to break the distribution into a mixture model where you have subdomains to model separately. And one way that you can do that when you don't have labels is via clustering, right? So you want to do some clustering in this image, but you see that if you apply normal clustering methods like k-means or any algorithm like that, there will be no constraints on how these clusters look like spatially. So you're just looking at the feature space, the colors of the image, and because you're just looking into the feature space and you don't know where the sample is coming from, you'll be like getting these clusters that are everywhere. They're just spread everywhere, right? So you have a cluster of yellow, but yellow is everywhere. You have a cluster of black, a cluster of blue, and so on. And so what we do is we develop new clustering algorithms that allow you to at least play with hyperparameters to control this spatial continuity, right? So there's one algorithm is called SLEEK. It's adapted from the image processing literature. It's called simple linear iterable clustering. It's one algorithm where you have a measure of distance, which is just a distance in the feature space combined with a distance in the physical space. And you have this hyperparameter m that weighs which is more important, right? So if you play around with m here, you get clusters that are more continuous or more focused on the features, right? So this is the kind of thing that we try to work on, and Geostats has, I think, 3 clustering methods that are specific for geospatial data. We have SLEEK, GHC, which is geostatistical hierarchical clustering, and GSC, which is geostatistical spectral clustering. And all these algorithms are being designed for geospatial data from scratch. They're not, again, traditional algorithms to apply in geospatial data. They are algorithms designed for geospatial data, right? So after like many years developing this framework, the Geostats.jl framework, we came up with this paper, which was the paper where we try to formalize some of these ideas and concepts, right? So it's a bit heavy on the notation and stuff, but the concept is super simple, right? So what is geostatistical learning, what we've been calling here, right? So geostatistical learning is when you have, again, all these elements that I was describing. You have a source geospatial domain, D sub S, and you have a source learning task, which is classification, regression, or anything like this. You have a target domain, D sub T, and a target learning task. And geostatistical learning consists of learning this task over the target domain, using the knowledge that we acquired while we were learning the model or the task TS in the source domain. So all these things are more explained in the paper, so if you need to get more, let's say, ideas of what's going on, if you want to chat after the talk, just come and we can nail down what these names are. But what we actually can do when we start to talk about these things very abstractly, because we define the elements very clearly, we can build learning models that are super sophisticated. Like, I mean, I don't know of any other framework in any other language that allow you to do these kinds of things that we are doing here directly. So here, I'm loading a building model, right? So you see this is like, my tablet is kind of dying to just visualize this thing, but this is like a building with complicated geometry. So you see triangles, quadrangles, whatever. And I want to do machine learning on top of this thing. So this is my mesh where I loaded a building model. Say, imagine you are loading a volcano or a coral reef or something from earth sciences or something that you are interested in your research. What we want to do is to basically create a pipeline that targets these things directly, right? Without having to do a lot of manual work. So for example, if you participated in the hands-on session on Monday, you know how to do the geodata science part, which is creating features, for example, on top of your mesh. So here I'm creating a table of features where I'm saying compute the area of all the elements in the mesh, compute the perimeter of all the elements in the mesh, compute the maximum inner angle of all the elements in the mesh. These are 3 features that I created on the fly, and I'm attaching these features to the mesh with the georef function, and this creates this geospatial data set where you see like triangles as geometries and 3 new features created just now, right? Now I want to visualize this. It's the same code as we had before, right? So I have these Mackie ways of visualizing, right, this domain. So I say visualize the domain of my data, coloring by the area. So that's the first one here. So if you zoom here, you see that these elements are colored by area now. This one is colored by perimeter, and this one is colored by maximum inner angle. So I've created 3 features on top of this geospatial domain. You can imagine like a satellite image or a 3D volcano model, whatever that is. And now I want to, for example, create like a training and a test set, right? So artificially what I'll do here, I'll just like split this geospatial domain into 2 pieces. And for that, I'll just choose a threshold tau, which I will apply to perform a group by operation. So I use that transform operation on my geospatial data set to create a group column, which is just wherever the perimeter is greater than threshold, group 1, wherever it's group 2. And then I'll just, for the sake of like example, I'll create a new column that's called stress, which is 1 over the area of the element. Just like saying like I have a force of unit 1. And then I created these 2 new columns, right? So you see here I had area, perimeter, and angle. Now I have group and stress. And what I can do now is group by this group variable, right? So I'll group my building by the group feature. This will create 2 subsets, the source and the target, as I'm calling here is a geospatial partition. and I can plot the two, right? So I can just come here and say, visualize the domain of the source with the color royal blue, and the domain of the target with gray, right? So if I zoom here, I subdivided my domain to elements that are in group 1, and here are, let's say, the pieces of the building in group 2. Now I want to train the model in group 1 and predict in group 2, right? So what I will do, I will just follow the same recipe I've shown above. So I'll create a regression task that maps area, perimeter, and angle to stress. I'm just creating this synthetic example, right? And I'll define my geostatistical learning problem that trains in the building parts that are in group 1 and predicts in the building parts in group 2. And that's the task T that I specified. I load again a decision tree, create the strategy to just learn point by point and solve. And this creates my estimated building with stress, right? So I can just go here and plot the actual value of stress that I've hidden, right? And the value predicted by the decision tree. As you see, like the colors are different, and that's to, again, emphasize that if you just apply these models that are not designed for geospatial data, and you apply it point by point, you don't do anything extra, you fail to capture this geospatial information here, which is volume, right? So when you train a model that you have a variable that's measured, let's say on 1 kilometer scale, and another pixel is like 10 kilometer scale, these are different things. The process is averaged, right? So just training a model like blindly like this without considering the size of the pixel or the size of the elements, you're going to be biasing your answer to something else, right? So that's what I created this example just to show that we need to customize these learning models even more. Like we need to create new models that take this support information into account. So there are some challenges in terms of research and in terms of technology that we're trying to address over the years, and we got a lot far already, but there are many things to do still. For example, we want to take into account the fact that the distance that we compute should be geodesics, right? So we're not computing straight lines. Sometimes these models are very curved. We have geometries that are curved surfaces, and in order to compute geospatial correlation, for example, we would like to follow the distance along the curve and not straight lines. This also is related, as I mentioned, to adequate correlation structures on manifolds, because correlation behaves differently when you have curved surfaces, so you cannot just assume that you can compute variograms and correlation functions as you usually do with flat 2D maps, right? So there are challenges, mathematical challenges in that direction. And specifically, if you talk about the climate and all the challenges we have in global scale, I think we want to also target some of these learning models on the sphere directly, right? So treating this sphere as like a curved geometry with specific topology and so on and so forth, and designing learning models on top of this object instead of just flattening out into a projection system and working there and coming back. I mean, I have a lot of more to say about these things, but I'm currently, as I say, I'm currently working at this company, Arpeggio, that I founded a month ago, where we are trying to evolve this technology even further with client use cases. So if you have any case and any interest in developing these things further, just reach out at this email and website. So feel free to contact. And if you have questions or anything, just feel free to ask as well.
We still have some minutes. We can discuss whatever you think is relevant. Do you have any questions? In the chat, maybe there's some. Can you see?
In the chat, let's see if there is any here. Stop sharing. There is a chat. Oh, it's just.
Okay. Well, I think we can proceed then. Thank you very much, Julio.
No problem.
Martin, are you ready?
I guess so.
Take your time.
Stop sharing. Let me stop sharing.
Easy, I think you.
It's fine. I'm still sharing on. Because of the connector. Sorry. you need
No, I have
mine.
a report.
If I don't get myself.
Take care.
Oh, good.
We're lucky.
Okay, so moving to the hands-on session 2.2, processing LiDAR elevation point clouds using vector data in Julia with Martin Pronk. Martin Pronk is a researcher at Delft and an external PhD candidate at the Delft University of Technology. Good, I've been there already.
Nice.
Yes, he holds a MSc in Geomatics and a BSc in Architecture, both from the Delft University of Technology. His research concerns elevation modeling, especially in lowlands prone to coastal flooding. He aims to combine his interests in remote sensing and software engineering for societal impact. He promotes open and reproducible research and is the author of several open source software packages for handling geospatial data written in the Julia programming language. His work often involves handling trillions of elevation measurements, requiring a careful selection and design of both spatial storage formats and processing algorithms. Currently, he works on applying data from ICESat-2, a LiDAR satellite, on global elevation models. Thank you. Whenever you're ready.
Thanks. Let me also start the Zoom thing.
Mm-hmm. Exactly.
Can you confirm that on Zoom you are seeing my screen?
Yes, perfect.
Okay, thanks. So, hands-on session on processing LiDAR point clouds. I'll do a bit of an introduction to LiDAR. I'm not sure how many of you are familiar with actually LiDAR datasets. Not at all, I see, so good. And then afterwards we'll dive into some future notebooks to actually handle that dataset, and we'll both be showcasing geodata frames, a package for saving and reading spatial tables, shapefiles, geo packages, that kind of stuff. And I'll showcase GeoInterface, which is an API package that enables hopefully seamless geospatial operations between different types of geometries in Julia, because everyone has their own favorite type of geometry. But before all that, I would like to ask you to go to the JuliaEO repository, do a Git pull. I think the latest update was an hour ago, so you can decide whether it's up to date or not. And then I would ask you to start a Jupyter Notebook session for this name right here, and then run the first cell. Because the package update and package add, there's a long list of packages that I want to use, and I'm not sure how long it takes, but I think it's good to start before I go to the introduction to LiDAR itself. I'm sorry for the Zoom bar, I'm not sure how to disable that. Anyway, okay, then a bit about myself. Like you said already, I have a background in geomatics. I work on Delft in the Netherlands. It's a research institute, similar like you have here. It's slightly bigger, but very similar goals. And apart from that, since a year, I'm also an external PhD candidate at TU Delft. And my topic is around global terrain modeling using spaceborne LiDAR. And I'll touch upon that topic later in this presentation. So, Delft, I've been working there for 7 years. Our mission is basically enabling Delta life, so trying to stay alive in cities, in the global deltas of the world, while there's flooding, sea level rise, and all these other problems. Flooding here in Mumbai. So it's about prediction, modeling. We also have large physical models to do these estimations. And for most of these problems, to tackle these problems, you need a very good elevation data set. Otherwise, you're nowhere. Because if you don't know how high somewhere is or what the slope is, you cannot answer these topics. So elevation data is my key topic and my main research interest. And happily I'm using Julia for that. I think one of the pressing problems, for example, is sea level rise. You have a beautiful, infamous island here, It's a bikini atoll, so it's known for its atomic tests back when. But also, you can see it here. It's basically a coral reef island. There's a bit of sand, there are a few trees, but this island is not higher than 2 meters at most. So if we do nothing about sea level rise, and probably for this island that won't happen, this island will probably be swallowed in our lifetimes. Unluckily, our global data sets, in terms of elevation, they often measure the surface. Surface meaning top of trees and buildings, or they penetrate somewhat into canopy. So if you would ask a current global data set of elevation how high this island is, it will tell you it's like 20 meters high in the middle of the island. So that's quite incompatible with doing analyses like this. So for elevation data, you will always go back to LiDAR. And LiDAR is light detection ranging. So it's like radar. I think we have a sort of running joke in all the LiDAR papers and books that they make the most awful pictures of how LiDAR works. Because you probably want to reinvent something yourself, and then you take a house there and an airplane there. I mean, LiDAR is not flown from sort of Boeing. It's often a Cessna or something. But anyway, LiDAR, it's basically you take a laser, and it can be on a total station just next to you, ranging around. It can be on an airplane. Airplane is the most common platform, but nowadays you also have drones. Slowly getting there, it's quite hard to get a drone stable enough to do these measurements. And in the end, we also have satellites now with LiDAR. So the technique in itself is actually, well, it's quite straightforward. You take a laser, you point it somewhere, you measure the return, and then you have a time step, so how long it took for that laser pulse to come back. You divide it by 2, you know the speed of light, and then you have a distance. Of course, for moving and flying airborne platforms, it's quite a bit more difficult and involved, but essentially that's what it is. It's a range measurement. And what you get in the end are many, many thousands, or hundreds of thousands, millions of thousands of point measurements. And these measurements, they can be anywhere, and they both measure trees, but they also penetrate canopy. Because laser, just like if you shine a flashlight on a wall, it has a very small footprint if you fly from an airplane, so it can actually, just like if you're underneath a tree, you will still see some sunlight through it. In the same way, LiDAR will reach the terrain. So this is one of the few active techniques that will actually reach the ground, which is why it's such a great technique. If you measure the LiDAR return pulse, it's actually measuring the wave. And depending on how that wave is measured in the airplane, big active instrument, you can either decide of storing the full waveform, so that's full waveform LiDAR. I won't go into that, but you also have those. Often what you get is discretized LiDAR. They take the full waveform that's measured from the laser pulse, and they say on the peaks of that waveform, that's one measurement. That's one big, strong reflection. So then you get detected echoes, and then you would result in 2 points in this case. So that would be 1 for the tree, and it doesn't have to be on the top of the tree, and 1 on the ground. And depending on probably your contract with the LiDAR provider or the some types, you can get many more attributes. It's not only X and Y and Z, it would be the intensity of that peak. There can be RGB, sometimes there are optical images taken while flying, because it's very cheap to also have a camera next to the system if you're already flying around the country. And there's the interesting thing of return number and number of returns. So for this pulse, you get 2 independent points, but since they belong to the same pulse, there will be 2 number of returns for these 2 points, and return number 1 and 2. And that's a way of also saying last return, which would probably be the ground, if you can reach it. As I said before, there are many laser pulses. We're talking about kilohertz often flying around, and you fly around for a few hours. So many points, big data sets. And all these measurements, they often have centimeter accuracies. Depends on your flying height, type of laser, but it's quite accurate. So unfortunately, very great technique. It's really quite expensive to do this. Mostly because you probably need to put it on a plane and start flying around. And you probably want to make a flight plan, so your airplane will fly around in a certain zigzag pattern so that it has covered the whole Earth. And that's an expensive process. It will, for a country, it will take you millions. And it means that only, let's say, rich countries have done this in the past, made a national elevation data set based on LiDAR, and then also opened it. There are probably some countries who have done this and not opened it, because that's another step. So if you see the distribution, this is Open Topography. It's an online portal, US based, so they basically try to take in all the US LiDAR data and have some processing tools available for that. Loads of dots in US and all the US constituencies. There's a large part in Europe. I put some pink dots of my own there. So I'm from the Netherlands. The Netherlands does have an open LiDAR dataset where actually, I think last week we published the full AHN4 version. So that's the 4th version of our national LiDAR model. So Europe is following along. But basically, the rest of the world, especially Africa, South America, and South Asia, there are no open source LiDAR datasets. So basically, we don't have a good terrain measurement in the rest of the world. It's one of the problems I hope to tackle in my PhD, but this is something that's very important. Because if you want to do flooding in Indonesia, you probably have to fly LiDAR, because there's no good other datasets available. Questions so far about LiDAR and the technique itself? Cool. Because then I like to talk about space LiDAR, which is my favorite topic. So like I said, LiDAR, just lasers. There's terrestrial use cases on a total station, but LiDAR is now also being integrated in cars, self-driving cars. You want to have an active technique to pinpoint people changing modes. It's actually very interesting, I think. In terms of LiDAR technology, self-driving cars are really driving the techniques forward, because in a self-driving car you need to measure a point cloud and then also classify the same point cloud within a millisecond or so, because you want to know that that point is a person or something else. So these LiDAR techniques are getting cheaper and cheaper based on the car technology. Then there's airborne LiDAR, so that's from an airplane, and that's the most default one and especially useful for elevation models. And then since, I'd say, the end of 2018, there has been an earlier one available, but really, ISAT-2 and JEDI are 2 LiDAR satellites. So they put a laser on top of a satellite. And that's great, because then suddenly we have LiDAR globally. But, and that's a big but, as you can imagine, an airplane can fly around in circles, patterns, and whatever you want. But if you want to do the same, you cannot do the same for a satellite, essentially. So there are major differences. For airborne, you can pinpoint the laser. You can try to point it a bit. You can change direction. In a satellite, you don't want moving components, essentially. It can break down and you can't repair it. So what happens is that you kind of move the laser pointer. Also, instead of flying 1 kilometer above the ground, you're now 500 kilometers above the ground. So you need a way different laser to actually still have some good footprint on the Earth. And it zips by at 5,000 kilometers an hour, yeah. It's crazy fast. So these are interesting technical considerations, but the biggest one is that it's the area coverage. So with terrestrial and airborne LiDAR, you're making sure that you cover everything based on your flight plan or other considerations. For spaceborne LiDAR, you just have to be lucky. It will zip past overhead, you have an overpass, you have some measurements, but it will never reach full ground coverage. I will show a picture later. So these are roughly the orbits of these 2 missions that I'm using in my own research, and they're very useful, I think. ISAT-2, it's meant to investigate ice sheets. So whether the ice packs moving, melting, etc. They're very good at detecting ice lakes, for example, which is an indication of melting. And there's JEDI, which is a full waveform LiDAR. It's attached to the ISS, the International Space Station, and it's actually meant for measuring the biosphere, actually biomass and such in the tropics. But luckily for us, I'd say They're both NASA missions, and they decided not to simply turn the laser off when there are not over ice or tropical forests. They leave it on, so we have measurements all along these orbits. But the big drawback is the coverage itself. So compared to radar, and we've seen a lot of radar processing already in this workshops, is that it's basically, it takes an image and it's probably 50 by 50 kilometers wide, something like that. So after, I'd say, a few months of orbiting, you'll probably have full coverage of the Earth, because all these pictures are overlapping, and eventually you have at least a single measurement everywhere. I think I remember one presentation that said you have at least, what is it, a few hundred tandem X measurements or so. Great stuff. But since this is lighter, it actually it has a footprint not of 50 by 50 kilometers, it's not an image, it's a single point measurement, and it's roughly 20 meters on the ground. So maybe if you have a ISAT 2 point, if it's an XYZ thing, it would probably have measured something in this room. And you can imagine that with such a footprint, you will never completely measure the whole Earth. There will always be huge gaps. So these are two, this is one ISAT overpass and one JEDI overpass. So ISAT is the vertical ones, almost vertical, and JEDI are the more diagonal ones. You see they have multiple beams. It's not a single laser pulse, but it's actually laser pulses and beams. And this is basically the pattern that you get on the ground. ISAT has a smaller footprint, let's say 70 meters. JEDI has a slightly larger footprint of 25 meters on the ground. And the difference is in beam patterns. So JEDI is nicely spread out. Every 800 meters there's a beam on the ground. While ISAT 2, they really wanted to bring well, beam pairs close together, 90 meters in between. And that means they can measure slopes on certain surfaces, which was of interest to them for science. So this is how your data would look like if you load it into QGIS.
What are these gaps?
This gaps is basically, this is a single overpass. And of course this will fill up, so you probably have a few...
I mean in the trail itself, like there are like the specks of like missing, like you see like...
Oh right, yeah, so there are strong and weak beams. Basically what they do, they split the laser beam into multiple beams, and that's a way of getting more measurements. But of course it has less laser power, so it probably won't penetrate deeply into a forest. So it's a trade-off. So what you see for ISAT, the left track here is the weaker beam, and then you don't always measure the same thing. For example, it's influenced by the sun, but also clouds. It can probably penetrate the cloud, but it will skew your measurement. So I filtered out the low quality measurements here. And sometimes they're not even measurements, because there has to be a reflection back to the sunlight. So that's why there's missing data. And yeah, same for JEDI. I believe this is the strong beams of JEDI, and those for the weaker beams, and you can see that indeed in the coverage. Yeah. So this is nice to have. And if you combine this over time, because these have been launched, these two missions have been launched at the end of 2018. We're now 4 years, 4 years of data. They're nearing probably the end of their life as well, these missions. I think JEDI got an extension on the ISS, because basically it's a module you plug in on one of the, I think the Japanese science module. I believe they're now lobbying to get an extension, and another one actually. And ISAT is basically probably continuing as long as their laser is firing. Eventually it will burn out. For the ISAT 1 mission, it was 7 years. So if you combine this over time, you get pictures like this. So there are many, many overpasses. This is an older one. I think this is a picture from 2020 when I made this. It's over Vietnam. You see there are still large gaps of multiple kilometers in between measurements. And this is one I made more recently. There's only a fraction of JEDI and ISAT data, but you can see, especially JEDI is covering the Earth nicely, although of course because it's attached to the ISS, it's limited to roughly 56 degrees. So this is the big drawback of Space LiDAR. If you have a measurement, it's great, because it's probably the first terrain measurement that's ever been done on that point of the Earth. If you have no measurements, you're out of luck. Then a little bit about the data handling, because this is the package I wrote, spacelighter.gl. It's basically to fix this problem I had. This is a NASA, these are NASA datasets, so they're provided by NASA on their distribution archives. And these are all H5 files. I'm not sure if you're familiar with them. They're like the basis of netcdf files. And they come, so it's not a shape file or a geo package. Binary file with many, many attributes, all array things. So you need to be able to convert this. So I think in the second notebook I will show you how to use the Julia package to convert this H5 file into a simple shape file or data frame actually. And good to know, these datasets, they're getting really, really large. JEDI, I think my estimation of the JEDI XYZ dataset that you could use instantly, it's probably 40 terabytes at the moment. ISAT has aggregated versions, so if you go to the raw version, I think you're at a petabyte right now, so that's, you can only use it on a smaller area in the world, or have a huge cluster or contact with NASA. The aggregated version is probably 20 terabytes. So, well, good data sizes, I'd say. And good to know there's an open altimetry web service, which makes it easy if you just want, you can go there, openaltimetry.org. You can do a very small bounding box selection, and you can see where there's data and where not. So that's a good way of inspecting data before you go into detail with the Julia package and then eventually find out there's no data altogether. And lately NASA has been improving the data access. So they're now also putting this data online in S3 buckets. That sometimes makes it way easier, especially if you want to process this amount of data. You probably just want to process it in Amazon EC2 instead of downloading it to your cluster or workstation. I've used this data together with some colleagues of mine in a paper. So we made a global coastal terrain model, but a very coarse terrain model at a 5 kilometer resolution or even 1 kilometer resolution. And I'd say, but that's the first really terrain measured elevation model. Other elevation models just, they will measure all the trees that are here in the Everglades. This is part of Florida. So it's and a nice recent paper by my colleagues who used the same data set to show that sea level rise will be worst for the first meter of sea level rise, because that will inundate most. And the second sea level rise from, let's say, a meter to 2 meters won't do so much impact anymore. Okay, then this was the lighter introduction, let's say. So I'll move to the Jupyter notebooks. Any questions thus far? Okay. So I have 3 notebooks. One is basically handling airborne LiDAR. I've provided in the JuliaEO repository a small LAS file, LAZ. It's an AHM4 sample, which I completely decimated to make it as small as possible while still being useful. The second one is a very small introduction to my space LiDAR package. It's just a utility package. It's basically getting the data in a data frame, and then it's up to you what you want to do with it. And the last notebook, which might be the most interesting to you in a generic sense, is showcasing GeoInterface and GeoData frames. I will be using GeoInterface and GeoData frames a bit in the previous 2 notebooks, but the last one is the more technical in-depth one. I've used all Jupyter notebooks because I thought seeing the latencies we all had in Pluto notebooks. I do like Pluto notebooks, don't get me wrong, but they might be just a bit too slow. So yeah, let's switch. Forgive me, I will be sitting down because I have to keep clicking and typing.
Sorry, I have a question maybe.
Yeah, sure.
Before you start. Do you know if it's already being used like this type of LiDAR dataset from Spaceboard to increase the accuracy of already available and a bit old datasets about elevation like SRTM that I remember it was 30 meters?
Yeah.
And that's the public use, I think, is the best still, if I'm not wrong. I used to do it, work on that like some years ago.
Sure. So yes, you can improve the existing elevation models because they are radar-based, they are full coverage, and then use space LiDAR to improve it. That would be the topic essentially of my PhD. Of course, I'm not the only one. So I think the best current radar model is actually Copernicus DEM.
Okay.
It's based on TandemX. Basically, you have the TandemX mission, then Airbus made World DEM out of it, and then now ESA bought World DEM and republished it as Copernicus DEM. So that's the 30-meter global elevation model. I'd say it's by far the best open model. So also simply because SATM is from 2000.
Yeah.
So TandemX has been collected for at least this elevation data set, I think around 2012 to 2015 or so. So it's also 15 years newer. And you can see that TandemX is actually, 10 meters, 12 meters actually. So 30 meters is resampled, it has been coarsened, but you can still see way more details than SATM. So I'd say if you want to use an elevation model now, use Copernicus DEM. And there have been already, I think if you search literature, several improved elevation models that try to sometimes use ISAT. I think most it's ISAT. JEDI is a bit, slightly more outliers in JEDI that are harder to filter out than in ISAT. So there have been improved elevation models. Okay, so I go to my browser now to have the notebooks open. Does anyone have problems with actually opening the notebooks, or did you run into errors when running the package add or update?
I cannot install a package. So I'm trying to do it offline.
Okay, which package can't you install, or you can't install it?
It says unsatisfiable requirements detected for package space LiDAR.
Okay, so that's probably your existing environment, and then some of the dependencies want to use a newer, Space LiDAR probably wants to use a newer dependency than you have.
Okay, alright, I'm updating now everything, so we'll see in a few seconds.
Felix, if you could help, that would be great.
Yeah, in the package that I also release just that servers. Because it very useful.
You can also just remove Space LiDAR from this package add.
Right, let's see what is happening. Unfortunately, the internet is not faster, so it will take some time.
Okay, so I put all the packages I will be using in here, which is probably a lot, and then it's a bit of a, well, it says something about the state of the package. I'm using point cloud rasterizers here, which is not even registered. Yes?
I think you're missing one, data frames, because I got an error saying I was missing that package.
Fair enough.
Geostat server also.
I think I removed geostats from...
Because after this you are putting using geostat servers, so...
You're right. I wanted to be nice to you, but I didn't get to it. You can remove those invocations, and if space LiDARs are running out, you can also remove it, because it only concerns the second notebook. I just put all of them here to have it installed before we start. Okay, so I'd say if something errors out, just try to remove it from the command line, and then we'll see. So LiDAR point clouds. In the files, I have vlieland.las over here, and that's the .las format is a point cloud format. So it's I think the ASPRS institution, they define certain formats for storing point clouds. And then I believe it was Martin Isenberg, who sadly passed away, who made a compressed file format out of that. And that has become the de facto standard for storing point clouds from airborne LiDAR. And these files are often very big, especially if it's a national data set. I understood that Portugal will be hosting a national elevation dataset, or making one, in the coming year. So I can imagine that after a national LiDAR survey, they will be cut into map tiles, let's say 1 by 1 degree, or depending on the map size of your national map. But that will probably be a tile of, let's say, kilometer by kilometer. Such a file will probably be a few gigabytes compressed. And uncompressed, it will be tens of gigabytes. So these files probably are too big to fit in working memory for the computer. So that's why I wrote a package, point cloud rasterizer, which basically is able to iterate over those point clouds without storing them all in memory. It's a bit slower because I have to pass over all the data twice, but it could handle larger than memory point clouds in that sense. So let's start with using the LasIO package. So there are many packages like this that basically say extension io.gl. So this package is purely for opening LAS files. I'm using Julia 1.8.5, but I'm not running in Docker, but if you're running Docker and using 1.8.4, it should also work. Okay, and what we then get back is a LasIO dataset. So this is lazy. It's actually using the LasZip library. Can I help anyone, by the way, because there's a lot of talking?
No, I think for me it's just the computers
Yeah,
down
it's
things. So
super slow.
yeah.
Okay. This is just lazily loading. It's not loading all the points into memory. It's just opening the file. It's using the LasZip C++ library in the background. So we can try to see how this looks like. I'm decimating by 100, because otherwise you're plotting, what is it? This is only 500,000 points, and this is already a very decimated sample of the AHM4. Normally, we're talking about millions and billions of points. As you can see, well, very nice that the plots interface works on this. It's not really useful to try to do a 3D plot of point clouds. There are probably too many points for you to plot nicely. So you might want to try Maki, but you could run out of memory. So what you want to do is to always, or at least that's the pragmatic approach, I'd say, is try to rasterize your point cloud. Because an image is much easier to display and manipulate than all those points. So let's do that. But before, if you want to look at the points and inspect them, LasIO implements the tables.gl interface. So you can just use data frames. You could also use another tables package. And if you call that, then you get a nice table with all the points. And then you have some more columns. So you can see the geometry is stored as a static array of size 3 actually. But you also see that we have an intensity, we have the return number of returns. There's a scan direction, which is actually the angle of the laser, which is making. There's moving parts. And there are attributes like edge of flight line. There's even a classification in here. So depending on, I guess, the contract with the LiDAR provider, for Portugal it could mean that the data set that you download maybe in a year's time could already be classified. And then it would depend on how many classifications you get. I know that the Dutch datasets have once been sent to, I think, India to classify them in really many classes. I think they had individual classifications for certain objects on a farm. That might be a bit crazy. Other classifications just include water and ground. That's, I think, one of the simpler ones. So this is already classified, but we're going to imagine that it's not and try to do a classification ourselves to create a DTM essentially out of it. But if you don't want to do that, this is a data frame with everything in there. So you could do all your own analysis on this object. It's a big table, so scrolling. So I talked about number of returns before, because LiDAR can penetrate canopy and you can have multiple reflections. So if you plot or make a histogram of the number of returns, you actually see that, well, most of the data has a single return number. So just reflected, bounced off, that was all you got. Or for some cases, you get 2 reflections, and even lesser cases 3, sometimes even 4. And 5 is apparently in there, but almost invisible. This is also depending on your laser strength. So I think newer lasers can get you even more reflections. I'd say 2, 3, 4, 5 here, so everything above 1 probably indicates that you're measuring canopy, because there are not many objects that you can actually penetrate in a single laser beam and you get multiple reflections back. It's either probably water. If you have a green laser, you could actually penetrate the water column, so you could reflect off the water surface, then reflect on some of the turbidity in the water itself, and hopefully eventually reflect off the bottom. So that could happen as well. So these kind of objects you're measuring. Given this table, this is actually the first demonstration of geodata frames. Not telling you anything about it, but essentially we provide geodata frames with the table, data frame, and we save it to freeland.geo package. I'm not sure how many of you are familiar with geo package. I mean, shapefile must just be, we must move away from shapefiles, I guess. It's an older format that's in many ways, well, we know better now, I'd say. So geo package is a nice one, but you even have GeoParquet now, and we're going to geo arrows. So this is basically how data frames work. It's a one-liner. It just takes a data frame with a geospatial column, which is the geometry column of those static arrays. Note that a geo package, most of the geospatial formats are not compressed. You could probably zip them and get some compression, but natively they're not compressed, meaning they will be much bigger than the original last file. So we're storing exactly the same information, maybe even a little bit less. So the last file is only 7% of the GeoPackage file size. So for these point clouds, don't try to save them all to shapefile or GeoPackage. You will just run out of storage space. Okay, so that's how you basically load a point cloud. So now let's try to classify it. And I'm using point cloud rasterizers. This is a non-registered package by Deltaris. As you can see at the beginning of the Jupyter notebook, we actually added it with the GitHub URL. And I imagine you could also do something like this yourself. Just develop packages on your own GitHub repo or your or other Git instances, and then add them. Nowadays, you can even add your own registry by adding your organization as a Git URL, and then you can work with packages without registering them in the public Julia repository. It could be useful for a research institute. There's a question.
Yeah, no, I'll just add something to it. It's actually quite nice because you don't have to make the repository public. So if it's like a restricted GitHub repo, we'll just ask for the login credentials. So that can be really nice for some organizations if you're not allowed to share code.
Happily, we believe at Deltaris, we believe in open source. We always say dare to share. Of course, you always have friction, and in some cases you need to be on a private repo. But it is indeed very nice that the packages for Julia just work with Git out of the box. Anyway, moving to the point cloud rasterizers. So what we're trying to do is we have all these points. We're basically going to inspect each point. We're going to define a raster, so a certain bounding box and a certain cell size that defines a spatial raster. And for each point, we're going to determine in which cell that point would intersect with. So in which point cell it would fall. We do that for all points. And then we have an index, we have a lookup. So, because point 1 would fall in cell 2 and point 3 would fall in another cell. And that's a structure we could also manipulate. And it's actually something that's okay to store in memory. It's not duplicating the whole point cloud, it's not storing all kinds of vectors, it's just a large list of integers. So this is the invocation, we just call index on the data set. So this actually works directly on the JuliaEO dataset, but it should work for any multi-point geometry. I'll come back to that later in the geo interface session. We provide it with cell sizes, which is just 1 by 1 here. This of course depends on your CRS of your point cloud. And in this case I know this is the Dutch elevation model, so this is the Dutch coordinate reference system. And I provide that directly here with geo-format types. So this is the first introduction of geo-format types. It's just a wrapper package. I think Rafael Schouten made it. You all know him by now. And essentially what it does, or what we determined, is often we were passing strings or numbers around to determine coordinate reference systems. Like I'm saying 4326 for WUGS84. So geo-format types just wraps those integers and strings into an actual type that we can dispatch on and say, look, this is not a random string of foo, this is actually a description of a well-known text of a coordinate reference system. So this is the way how you would define an EPSG reference. This would be the Dutch coordinate reference system, but you're probably more familiar with just putting 4326 there. So I hope this is, there are not many points in here, so that's why it's quite fast. But this already would, on normal point clouds, this would already take a few minutes and maybe even hours on large tiles. You will get a progress bar. So this is actually, what we now have is basically a raster of counts. So if we plot that attribute of the index, of course it's not showing anything. I need to. So what we see here is a rasterization of the point clouds purely based on the number of points falling into each cell of that raster. So you can actually see a little harbor here. And here there's clearly a larger clump of points, so that's probably trees. Because of the multiple returns over trees, you get more points in such an area. What you can also see that there's a very nice diagonal line in here. And this is a common pattern in airborne LiDAR datasets, where there are multiple flight lines by the plane, and they will also always overlap a little bit. So on this side is probably an overlapping part, and that's why you get twice as high as a point density than the part to the north. We can also say we don't want 1 by 1 meters. I decimated this data set, so I think this is the most high res you can get. But for the original data set, you could go to half a meter or even 25 centimeter cells. We can also, of course, go higher and then just make a much squarer block. You see almost black line here, and that's probably because the bounding box of the data set doesn't nicely align with the cell sizes I chose. So let's go back to 1 by 1 to actually identify features. It becomes a bit hard at 25 meters. So if we want to create a terrain model out of this, you want to actually ignore all the vegetation points, etc. So we're gonna start with only taking the last returns of the point clouds. And the last return, because previous returns are always higher by definition, we probably don't need them for the terrain. So we would define our own function, that is, and that would depend on the actual point object you're passing in. It could be anything. In JuliaEO, we know how the point looks like. So we make a function, it can be very even anonymous function if you want, that just takes a point, p, and then it compares the return number with the number of returns attribute of each point. So if the number of returns is 3, then only for return number 3, so the last point, this would actually say true. And then we can call filter on this index we build up with this function. It's actually very quick, and what it does is, again, loop over all the points, compares them, and if it's false, it would actually drop that count altogether. So you remove the index for that specific point. So if you then again plot the index purely on counts, you actually see that it's much more homogeneous because there are no multiple returns anymore. Moving on from that, the last function essentially that you want to apply in this rasterization of point clouds would be to reduce everything. You still have a cell, which essentially is a bucket of multiple points. I want to have one value for that cell. Then you can write it to a geodiff or your other raster format that you're interested in. So we need to apply a reducer to that. And then the reducer would be, we could choose a minimum. So just that would be the minimum of the elevation points that you get. But you could also provide your own function to determine what attribute you would want to reduce. You could provide a function that would choose to reduce on the intensity or some other weird thing. Well, let's first do the min raster reduce. And then we get a geoarray back. This is like rasters.gl. I have a similar package that I'm using here. We could also move to rasters. So now we can save this to geotiff or actually plot it. And this is the first time we actually see elevation in the point cloud. I think there's a bug in Jupyter notebooks with fully zoomed in plots. So you have to zoom in a little bit and then it shows up. So here we actually see the hardware is quite low, and then we actually see buildings here. You can even see that these buildings, typical in Holland, these are slanted roofs. Because it's a little bit orange in the middle. So ideally, a DTM, a terrain model, should have these buildings removed altogether. So let's do that. Any questions thus far? Is it working to follow along in the notebooks? Yes. Cool. I see there is also like 6 questions in the chat. Is there any pressing questions from the chat?
If you want to answer them, you.
Yeah, I can probably check them myself.
Ah, okay. So
This seems fine.
it's all right. It's okay.
Cool.
It was about the mic. They weren't hearing you, but they are now.
Okay. Via the camera then, directly.
Yeah, it's listening. Okay.
Yeah.
Yeah.
The white pixels on land are white because of the same elevation as water, or because it's missing data?
There are no elevation points inside that cell.
Okay.
And indeed, that also happens over water. LiDAR will reflect on water, but that will depend on the waves or, well, let's say the state of the water. So what you often see in water is that if the water gets more rough, so outside a bit of waves, there is always some angle that would reflect back to the airplane. If the water is perfectly level, you would see only returns on water directly underneath the airplane. So you can actually use LiDAR for water detection. We actually use it for water level measurements and even slopes in water levels. I forgot the English word for that. So that's why you don't see any points here. Normally over land, these white points would indicate that you're really on the edge with this resolution.
Okay.
This is probably still acceptable, but going to a higher resolution doesn't make sense for this data set because your source data isn't better than that. Okay. So we imported the package GeoArrayOps, and there are multiple terrain-like functions there, or for terrains. So there are like slopes in there to determine the slope based on elevation raster. But there are also filter functions. And these are morphological functions like opening and closing on images. And one of these functions is PMF. We can actually check the PMF functions. And that says, this is by the way the help function. I assume by now you're all familiar with it. So just question mark, just like in the Julia REPL on the command line. You get the help function of this function. So the PMF is a progressive morphological filter by Zhang back in 2003. And basically what it does, it takes a raster assumed an elevation raster, and you give it a certain slope, and then it's going to check for each cell whether all the cells around it are within that slope boundary. So if it's if you put a very low slope in there, most points will be removed if there is any variability in there. It's called progressive because the window size is increasing and increasing and increasing. And this works pretty well. There are simpler ones, but we'll just use this one for now. So we're going to input our minimum raster that we have. So with buildings, and I guess even some trees. These red things are trees. Or at least they don't look like terrain to me. And PMF is going to try to make an elevation raster that's like the maximum allowable surface that it could imagine based on the slopes. So we can just call that. And then we get a maximum raster back and also a Windows thing that we'll ignore now. And if we plot that maximum raster, we'll see that it's different. Everything is a slight bit higher because there's some level of allowance, of tolerance in this filter. We also see it's still allowing houses to be in there, so our window size is probably not large enough to completely filter them out. But what you also see is that there are probably these don't have roofs anymore. So this filter has a maximum in there that limits the elevation, even in the cases where these houses are. So we can use this for comparison with our other raster. And basically, we say from a terrain raster, we can just compare these elevations, and everything where our LiDAR raster is higher than this raster we now produced, we would indicate that as non-terrain. So this would be a binary classification by comparing it. Let's move on. We do see, however, that in this PMF, there are still houses. So we can try to improve this PMF filter a bit by providing better settings. So what I put in here is that I put in a better slope. I put the window size higher and some other parameters. So let's plot that again. And now we get a much better filter surface. So you still see more houses, but all these houses are way lower. So this filter is much stricter. However, it also probably keeps in the terrain features, like there are some dunes here. This is one of the islands in the Netherlands, by the way. So we're going to use this one. And we're going to use this raster to classify or filter again the point cloud index that we have. So we're going to create a new function, a new filter function. And now this filter function doesn't just take one point like before, but it also takes a raster value. So that would be train PR. And note that we're now saying geointerface.z on this point object. And this is the first time we're invoking geointerface. If I want to write it just looking on the points we had, so if I scroll all the way up, the points actually look like this static array and the field geometry. So if I want to write this specifically to this point cloud itself, I would write down, sorry for all the scrolling, I would write something like point geometry and then 3. That's what you would normally do if you only wanted to work for this specific type of geometry. If we want to use geointerface, geointerface has a function that basically gives me the Z attribute of your geometry given a point. So this is the same way, but writing in a much more generic manner. I'll come back to this in the last notebook. And what we define here is that the Z value of this point should be lower or equal to the raster value for which that point is in. So let's define that. And then we apply it. And then we not only filter the index, we also provide it with the max raster. I think this can be removed like this. And then we provide a terrain function. If we then plot the index.counts, we now see we actually removed almost all the points in all the houses. So this is an indication that a filter worked correctly. But, and that's a big but, we were slightly too strict actually. Because you can see that there's some weird black spots on the right hand side. And you can also see that this dike element, which was protecting the inner land from the harbor, which is at sea level, is also removed. So this is still too strict of a filter. I'm not going to improve it further, but these are this is an iterative process that really needs tuning depending on your landscape. So saying that we're happy, we can reduce this index. It's now completely filtered almost correctly. And then we say, let's use the mean to combine and reduce all these elevation values, and then we can plot it again. And then this is what you end up with. So this would be close to a DTM. The only problem here is that there are still holes in here. So you would now choose an algorithm to fill all these holes. I will skip that for now because I'm thinking I'm running out of time majorly. I'm not sure.
You have until 3:40.
Oh. Well, anyway, that's why I had, I think geostats would be a good candidate to actually use here. Because geostats has the many normal solvers like the IDW or other solvers like that. If we have more time, we can go back to that, but for now, I'd like to move on. I think I said we leave interpolating as an exercise. And this is a point that I also want to improve a bit further in the package itself. That would be one of my to-dos actually for coming days. So any questions so far about this point clouds notebook? Because this covered less I/O, less dataset. Now we're moving on to the Space Glider utility package.
I have actually one question.
Yeah.
So as I understand, we don't make a digital terrain model over the ocean, right? Over the water.
True.
And how to get rid of this noise, this kind of salt and pepper effect in the water here? How to clean this data?
Normally one would just use a vector mask. There's
So you probably use a vector mask and then remove everything that is in that vector, right?
right, yes.
Okay.
But it really depends. LiDAR classification is just a painful task because there are so many points. There are many ways of trying to do this automatically. It would be also, you could also apply machine learning. I think HN4 is actually partially automatically classified by machine learning. But there always are points that needs a bit of touching up. So I think in the Netherlands, all the houses, we have a very good public housing data set with all the building polygons. So that's an easy step of just classifying all the buildings or removing them from the DTM. For small water bodies, it's much harder. You can imagine that there sometimes are ships in this harbor and sometimes they're not. So that's not one clear way of doing that. You could also look at intensity, because probably most of these water points might have low intensity. If you have an RGB image, it's actually easy to say based on that RGB image to determine whether something is a water body or not. But these are all classification tasks, and it's not that easy. So I have no clear-cut answer for you.
Okay, thank you.
We have used these tools to basically generate DTMs in Indonesia, where we could fly LiDAR for certain parts of the small parts of the country. And then we could use this for basically hydrological modeling. But we only needed to classify ground there, and we're just happy with what we got.
Okay. I have a question. Maybe
Yeah.
it's a stupid question, but I'm seeing here like the minimum value would be close to 0 or 0, right? Which would
Yes.
be the black color. So when you convert the LiDAR data to the digital elevation data, so how does it find the 0? How does it know it's the 0 is the sea level?
That depends on the, of course, if you fly LiDAR from an airplane, it's actually probably all with GPS. So those coordinates would be in WS84 to the ellipsoid. And it's up to the LiDAR provider to properly reference that to your national data set, national datum. And that includes a vertical reference level.
I see.
So this has been translated for us to the Dutch national elevation, which is actually, I think, also the reference level for Europe right now, or some offset to it. So this is, yeah, this is based on the provider.
Okay, I see. Thank you.
And even here, 0 is a, 0 doesn't need to mean sea level. That's always the tricky part.
Okay.
It's just, it has been a reference level, has been chosen, it's based on something, often a fixed reference mark. I think historically, the Dutch reference level was to a lower water level in a harbor, because the low water level is what you want to use for your ships. If it's lower than that, you cannot pass in a certain channel. So it was a classification like that.
So
But
it's an additional thing you might have to play with a bit further to arrive at a good result, right?
Depending on your application, yes. But then I also always say it's better to have a good reference, documented reference, than try to do something yourself to make it nicely match, because probably no one can reproduce that and it becomes harder to interface with other data sets. Okay? Any more questions about this part? Cool. Then let's move on to the second notebook. This is a shorter one, but I'll showcase a few geo interface functions more. If I run this package update, I think it shouldn't do anything because we installed all the packages in the previous notebook. And this will make use of one of the HDF5 files I also put in the repository. It's one of the smallest ISET files I could find to actually match it. So, oh, it's actually pretty slow. I hope your internet is faster than this. No? Oh, there was a plots update. That will slow down everything for me. Anyway, I'm using the Space LiDAR package here. So this is a utility package. I talked about ISET and JEDI before. So this is a utility package to search and download and basically convert those HDF5 files to, let's say, a tables object, like a data frame. And it can do so for JEDI and ISET, and also for ISET1, which is an older mission. Less data, but could still be useful. So how you would use it is basically call search. You would define the mission, which is ISET. You could also put JEDI here. Then search for the data product. So this requires a bit of knowledge about the ISET products. There's, for example, 8006, and then you would look at ICE measurements. That's 8003, and that's much rawer data than this. And what we want to do here is provide a bounding box. And this is the first time I've shown extend. So this is the extends package. I think it was also written by Rafael. And this is basically a way of defining a bounding box. Just to get a common interface. Before I was using named tuples with min x, but then someone else was using a named tuple with x min, and those are not compatible. So we arrived at this, well, very simple format. You can still criticize it because it's using x and y and not latitude or longitude. But this extend is how you would define a bounding box. So you can provide this bounding box. From the top of my head in WS84, this would mean it's a 1 degree bounding box around this island. So if we call search, this actually calls NASA Earth Data Search. So that's a website where you can search it for manually, very useful. This is the API. And we see here, I'm happy that the internet actually works still. We get 183 ISET2 granules. And a granule is essentially a part of an orbit of ISET2. So And because we're interested in only small area, one granule essentially means one overpass over this area. We have, well, lots of them. Let's inspect one. Just scroll past this. So a single ISET granule, this type, it actually has a few fields. So what we're actually storing is the ID of the granule. That's the whole name with a date and some other information in there, .h5. It actually stores a link to a NASA data center, or actually the National Snow and Ice Data Center in the US. And based on the file name, we derive some attributes, some information. So from the file name, you can actually parse the date. These naming are standardized, so that's useful to filter further. And based on the search results, we also have a polygons that we store, which is this nested vector. This is actually a multi-polygon that defines the bounding box of this granule. If you normally use this with a good internet connection, you can now call download, or even download exclamation mark, the mutating version, on this granule. It will try to download this file from NASA, stores it locally, and then it will update the file link in this granule. So this granule will then point to your local file. Let's not do this, because this is probably a few hundred megabytes. And you also need credentials to actually download from NASA, so you need to have an Earth Data account. It's free to register, but you need to register anyhow, and I'm not sharing my credentials with you. But that's how you would do it. You can use the utility function spacelighter_netRC, exclamation mark, and that would write a small text file to your home directory with the username and password for this NASA server. And that's how tools like curl and wget and even downloads in Julia itself, they would use that file and use those credentials to log into the server to download the file. So I provided you with one of the smallest ISET granules I could find. Normally these are much larger. I think this is only a few MB. So we can use the utility function granule from file and then provide it with the file name. And then we get the exact same thing as we saw earlier, but now it actually has a reference to a local file. Might actually be nice to make it into an absolute path. I'm not sure. And this package, just like the JuliaEO package, and I think many other packages in the ecosystem, they implement the tables.gr interface. Basically meaning this is some sort of a table, so it implements a few functions that you can just call a very generic data frame on it, and it will automatically convert all that data on the fly into a table. And I think that's a very nice thing about Julia, all these nice interface definitions, because now at this moment you don't need to know anything about this HDF5 file. You don't need to inspect it, you just call it a table on it, and it will iterate through all this data, even iterate over the multiple tracks there are in that HDF5 file. And then you get the following back. So this is a table with longitude, latitude, we have a height, there's a height error, and some other attributes that are in this HDF5 file from NASA. And I think important one is of course longitude, latitude, and height, so X, Y, Z essentially. But it's also good to know there's a quality attribute. And if you want to use this data in your daily work, definitely filter on the quality. Because the non-quality ones, they're just really noisy, never use those. And you can of course do other manipulations based on these attributes. There's also a height reference field, which comes, I believe, from tandemx. So that's how a global DEM would look like. And often, of course, this ISET value is slightly lower than that, because ISET would penetrate the canopy, and whereas the global DEM would not. So we again have a table. This is the same actually like the JuliaEO. This is some sort of a point cloud. So we can also, well, let's first plot it to actually take a look at how it looks like. This is not over the Azores. I think the Azores one were too big. So if we call scatter on these columns, longitude, latitude, and color by the height, so we use Z color, we can see that these are the ISET tracks. We can also see that they're actually You can see a slight curve, as we would expect. And you would see that it covers a large range of latitude, actually. So these ice granules, they cover really a large part of the Earth. This is a very small one, but they take up, I think, to a quarter of the whole latitude you can have of the Earth in an orbit. So you really need to subset these data sets. You would filter the data frame to get to your location of interest. Even if you downloaded all these 183 granules for Tessera, you really need to subset the data for only Tessera, and you would probably be left with only 1% of the data. So always good to keep that in mind. I remember that JEDI data, the first version, they are now at version 2, but the first data set, they didn't subset their orbits in smaller subsections. And that's fine, but it meant that even if I want to download only a small part of the world, I would get a complete orbit of the Earth. So for downloading the Netherlands, I had to download 50% of all JEDI data ever, which was immense. They improved upon that, so they now have smaller parts. You still need to download a lot of data. So yeah, it's just a drawback of global data sets. We can also, of course, take a scatter plot in the other direction, so actually make a profile. And here you can see much more clearly that we're actually measuring elevation, and it seems that we're actually measuring a mountain or something, because we're going up to 2,000 meters. And I colored these by the different tracks. There are 6 tracks in total. It's good to note that even though these files look like they're slightly above 0, they're not referenced against mean sea level. So this comes back to the previous question about what is 0. This is referenced against the ellipsoid. So the WHGS 84 ellipsoid. That's very normal for, well, space data sets, I'd say. But you cannot just start comparing this with your local dam. Depending on where you are on the Earth, you have difference up to 50 meters compared to your local geoid. So you need to apply transformation here. So we can save this. So let's save this to, again, the geo package, my favorite file format. And unfortunately, because I haven't been able to do that yet, this is a table with longitude, latitude, and height. It doesn't specify geometry. So we need to create one based on those 3 columns. So we do that with calling geodataFrames create point, which is actually creating create point from ArcGDO. And we do that, of course, in a dotted notation, so this broadcasts over these 3 columns, these 3 arrays. And we write that to the geometry column. So this is just creating an extra column in the data frame, and then we call geodataFrames red. And nicely also specify the coordinate reference system. So this is now an extra invocation, an extra argument to geodataFrames. And again, geodataFrames just takes a table with the geometry column. It doesn't really care about what kind of geometry it is. Of course, it helps if it's ArcGDO, because it's geodataFrames itself uses ArcGDO in the backend, GDO itself to write a geopackage. So, and now you have something that you could open in QGIS or your favorite geospatial editor or editing system. Yes?
While saving, you got method errors because of type of ArcGDO geometry, in fact.
Did you update the
Yes.
all the packages?
Yeah.
Then I will come back to you later and check it. That's good to repeat, also from the previous lectures. If you run into something like this, that's still sometimes quite common. I think if you look at these packages over the past week, there have been multiple patch releases to fix small bugs like these. I love that making notebooks and doing these use cases actually enable me to also find these bugs and fix them. But this is still quite a young ecosystem, so you will find bugs. And also, I think in other languages, it's very clear that you can only do A with B. And here in Julia, we're providing interfaces, and we're basically saying we can accept anything. And there's so many combinations that you'll probably hit bugs because of that. So it's a strength, but it can also be a weakness, and because we're still so young, it's sometimes a bit painful. I think I fixed the bug recently, so might be still an update, but I'll come back to you later for that. And that's it about SpaceLider, because now you can, it's in a table, you saved it to another format, you can now use this as point data. So you can determine where maybe forests are, or whether your elevation model was wrong or not. Okay, any questions about this? Part that it didn't work with the data frame save?
Yeah, sure.
Yeah.
So you mentioned that this was the smallest excerpt that you could find just for demonstration purposes, right?
Yeah.
To your knowledge, what would it take to update the dam from these islands, like these 9 islands? Because we see, like on the mainland, on the continent,
yeah,
that on something like Google Earth Pro, you actually have like a very nice representation of the height.
Mm-hmm.
But when you go navigate to Azores, it's still like SRTM 30 meters, something like that.
Right.
So to your knowledge, what do you think can be done to improve that?
Well, that would be part of my own research, of course, in my own PhD. But I would say take Copernicus then. It's more recent and has a better spatial resolution. And then download maybe all ISAT ATOA data. And for these islands, that should be perfectly doable. It's just about trying to find a way of correcting Copernicus then for these ISAT points. And that really depends on your local topography. You don't have many very high forests, and even the forests that you have, from the limited seeing I've done of these islands, to be fair, they're not huge. So for example, in Indonesia we have problems because the forests can be, and sometimes even plantations, there are kilometers, there are hundreds of kilometers of forest. And here there's clumps of forest.
Yeah.
And most of it is actually agriculture, so that's quite flat. I do wonder, however, how all the small fences, the rock fences, will influence the elevation. So that's an interesting thing to check, actually.
Yeah, that's very interesting, actually.
But I think all ATL data, you should be able to do that on your laptop, providing you have, let's say, 10 gigabytes available.
Yeah, sure.
Something like that. That should be the case. Okay. Last notebook of the day, GeoInterface. So this will be slightly more technical. It can be really helpful for debugging geometries. You're trying to write more generic code. And if you implement a package in which you have geometry things yourself, it could be actually be beneficial to implement GeoInterface for your package geometries as a developer. Of course, I understand that's an advanced use case. So I'm using geodata frames, GeoInterface. I'm using downloads because I'm still cheating, and I will try to download a shapefile over the internet. It should be a small one, but fingers crossed. And I will be using shapefile. So there are many ways of reading data sets within Julia. LesIO, which I showed you, is actually a wrapper around C++ library to read those files. That's one way, and it means that in the background there's some other project actually compiling that code, writing a Julia wrapper around it, and that's all in the background, you don't notice it, but essentially when you do package add geodata frames, you'll be adding ArchGDAL, you'll be adding GDAL itself, and then GDAL_JOL, which is actually a compiled GDAL version. You probably know this from your Python experience, that if you want to install GDAL and other packages together, Python will not be happy about that. Or Conda will fail on some resolving. So Julia, I think, has very nicely fixed it. I'm not saying there will never be errors, but most of the time it's quite easy to install these binary dependencies without huge errors. So if this succeeded, you're actually having a Julia-specific GDAL library already installed, and actually a Proj one as well for project transformations. However, especially in the beginning, we disliked binary packages a bit. So if there was a chance that we could write a native Julia package, so pure native, no C calls, we did. So there's also shapefile, the shapefile package, which reads and almost writes, it's ongoing actually this week, also complete representations of shapefiles. It's the table, the DBF tables that's being updated right now. So there's also native solutions. And GeoDataFrames was basically inspired by, well, many help requests and issues on the ArchGDAL repository. ArchGDAL is a great tool. It makes all the GDAL calls for rasters and vectors much more Julian, but it could be involved a bit to use. Like writing a shapefile, you had to write, I think, maybe 10, maybe 20 lines, and there would often, if there were errors, there would be opaque errors. So I thought, let's make it into a one-liner. It's all using ArchGDAL in the background, but I just made it into a one-liner. So GeoDataFrames can read anything through GDAL. So basically all the GDAL drivers, shapefiles, geo packages, many other formats as well. It can read. So what we're doing here, first invocation, is actually downloading a zip. We use that using downloads.download, which is a built-in package in Julia. Hopefully you're familiar with it. I needed to do a little trick here so that GDAL understands what I'm doing. I'm renaming the downloaded file to shape.zip. So if now GDAL encounters this file, it knows it's actually a zipped shapefile, and then it can just open it without me having to unzip the data first and then pointing to the shapefile. So this is the first time, wow, that I have an error as well. So that's also using downloads. It's still erroring. There we go. So this is the first time I call geodataFrames.read. So you just provide it with a file name on your local file system. Like I showed you, it can actually be a zip file. And if you go to the documentation, you will also show you how to actually maybe load data from S3 or online location. It needs prefixes to the file name to actually get there. But basically all the functionality of GDAL is available via providing the file name. And again, we get a data frame. Now with another type of geometry. This is iGeometry, not from Apple, but from ArchGDAL. The I actually stands for interactive. Has to do with pointers and cleaning stuff. But this is basically the representation of the shapefile with attributes, all these columns here. You can see sometimes there's a question marks behind the name, the type here, and it means that some of the values in that column could be missing. Something to keep in mind when editing or using the data. So that's how easy it is to read shapefiles and other files in Julia. It should always be a one-liner, and otherwise we could do better, and please make an issue. Now I want to go a little bit into detail about how this all works and what you can do more with it. So let's call plot on the geometry column. I'm all doing this with plots.gl with the default backend. The plots.gl backend differs per operating system, so on Windows you might have a different backend than here on Mac. But you all should be able to produce a plot like this. So we also support essentially via GeoInterface as well, and these recipes for plotting, we can plot geometries onto a figure. And the rest, well, we can make a histogram of other tables, so this is all straightforward. But now let's look a little bit more into what the geometry actually looks like. So what we have here, we can, I export all the methods operating on geometries in ArchGDAL. So we can buffer the geometry with 1. And then we get a buffered polygon. So we're just making the polygon bigger. But this is a geodata specific method, actually using ArchGedo. And like I said before, it's better to write generic code and use geointerface.buffer. In the end, it will call the same method because ArchGedo implemented geointerface and will use that method. So we can actually say geointerface.buffer in the exact same way. And we apply this on the whole column. And we'll actually overwrite the column in the data frame. So let's do that and then plot it again. Do note that what I'm doing here is maybe you shouldn't do in your normal work, because this is a data frame or geospatial data in latitude, longitude, in degrees. So buffering with a degree is not what you think it is. It's not in meters, it's not the same everywhere. So this is purely for demonstration purposes. Don't sue me. And as you can see, around the equator, this looks sort of okay. Indonesia gets exploded with all its islands, and especially near the poles, everything gets quite blown up. So that's about basically using geodata frames and providing a geointerface function. And now I want to dive in, why geointerface? What's the real use case, and how does it work in practice? So there's the OGC, which is a standards body. They've provided many standards to use. And one of them was a description of how geometry should interlink, what type of geometries there are, and basically saying that a polygon, if you have a polygon actually consists of multiple rings. So a polygon with holes, a normal polygon would have one ring, basically a line string. And if you have a polygon with a hole, it will be 2 rings. And that's all nested. So we actually implemented that in a traits-based interface in Julia, trying to solve the problem of handling all these different types of geometries in Julia. As I said before, everyone has their own geometry type. I think meshes has its own types, and it goes into 3D, so it has a different use case. There's just the ArchGedo ones, which are direct translations of the GEDO code. There's Geometry Basics, which has been rewritten right now. That's a different use case altogether. Makey probably has its own types, and many other packages have their own definition of a geometry. And that's good, because it's probably optimal for the use case. There have been many discussions in the past about what a point should be. Is that a tuple of coordinates? And which type of coordinate do we allow? Or is it actually a vector of coordinates? In Space Glider, which I showed before, there's not actually a point because it's an attribute. There's an x, y, z or a latitude-longitude attribute that would virtually define a point. So we had basically enough of these discussions and just try to provide you with a set interface. So you have a set of functions that you can use, and that will unify everything. Because the problem here is, if we look at the geometry that we got back from geodata frames, we see here that apparently this is a polygon, so it has a nice print method, so it can show some of these coordinates. But if I actually want these coordinates as a vector or floats, I don't know what to do, right? Because this is iGeometry. I don't know anything about iGeometry, and probably neither do you. This is someone else's geometry. If we actually try to call the help function on it, this also works on existing instances of types. We see it's ArchGedo thing, and we see something polygon, so that's good. But we see it just has a pointer. So no way for me to actually retrieve coordinates. This is logical because it's actually calling into C library. So this is a very good use case for geointerface, because we can actually call all these kinds of functions. I'll provide an example. So the most upper function in geointerface is actually trying to see if this geometry implements geointerface. So the first question would be, is geometry? And if that's true, then we know that the package author of ArchGedo has implemented this, and then we can ask further questions. If this is false, we're out of luck, and maybe you should create an issue on the repository. So if this is true, we can ask further questions, and we can ask the geometry trait, and here we see it's a polygon. which we already saw before, so this is something we could infer. But we can ask further questions, like the number of coordinates, and we see this is a 2D geometry, so it just has x and y. There could also be 3, even 4, but that becomes a bit undefined. And we can also request all the coordinates of the geometry, and what we get back is a vector of a vector of a vector float. So this is a bit nasty maybe to work, but this is how this is defined essentially in many geometry formats. And you could save this directly to GeoJSON. So this is what you expect. And this is actually what I wanted. I wanted the vector of points, of numbers, and now I can work with this. However, this coordinates goal is actually hiding a bit of the details. So you can imagine you want only the line string of the polygon, or maybe a hole. So you want to delve into the geometry. And again, with the ArcGeo one, I don't know how to do that, but I know the geointerface methods. So I can actually also ask how many geometries are in this polygon. And I get back, I get 1. So it only has an outside ring, essentially. And then we can request that. So there's n geometries and get geometry. And I basically get, with that command, I get now a linear ring, which is what I expected. And that object also implements the geointerface. So this is going to nest and recurse all the way down. I'm actually going to show you all of that. So this linear ring that we got, it's a line string trait, so it's actually a line, what you're used to. And again, you can ask that line, how many geometries do you have? And we'll answer 472. So there are actually 472 points in that line. And like that, we can recurse, and we can again ask get geometry for the first point, and then we're going to get a point back. And we can request the coordinates of that point, and then we have a nice vector or float with the x and y attribute of basically the first point in that polygon. So this is how you now can inspect geometries for, I think, 10 custom geometries in the Julia ecosystem. And we're actively expanding the number of packages that implement GeoInterface. So if you use geometries, this is the package to know, or the link to have to the documentation. Any questions thus far? Yeah?
Yeah, so the geometry, it doesn't have any, the GeoInterface doesn't have anything with the coordinate reference system. That's separated in a different package.
Yes and no. Actually, if you see here, this actually says CRS,
right, yeah.
so you're quick. So I want to touch upon 2 other functions. There are actually many more in GeoInterface. I already showed you buffer, and there are other geospatial operations. But let's say 2 metadata functions are the extend and the CRS. And I've already shown you both, creating an extend object and creating a geoformat type CRS component. And so if you implement GeoInterface, you probably also want to implement extend and CRS on your geometry. And what you see here is that extend is implemented. So I get a bounding box back for this polygon with x and y. But you also see that how many times I even click this, I get nothing back here. It also does show nothing, but let's check it. It's nothing. So this method has not been implemented on an individual geometry. So yeah, sometimes that's just the case. That depends on the package implementation.
Yeah, I have the same with, so if you need a package that just handle like simple coordinates and do some simple coordinate transformations between reference systems, the ArcGDel is the easier way to, like this is only if you need to make your own points implementation and your own geometries.
if you're a package developer, you can implement GeoInterface on all the types that are geometries in your package. But of course, this has a user side. I'm basically the user now. So it's very useful for me to actually get coordinates back like this, or to get the CRS or the extent in my scripts. And the nice thing that it's quite generic, because I basically can switch my backend for shapefile or GeoDataFrame, but even less I/O and even SpaceLighter later on, and my code would still work. But of course, you have to check that not everything does have to be implemented. Sometimes the CRS is just unknown. Okay, I think I showed writing with GeoDataFrames before, but let's do it again. So we basically loaded this data frame, we buffered the geometry, and we can again write it. So now we write it to test2.shape. Write it with a CRS, just for the fun of it. And you can also provide a driver option if you want to do exotic drivers, and you can pass arguments to GDO. That's all in the documentation. But I want to show you that GeoDataFrames actually accepts any tables.gl table and any GeoInterface implemented geometries. So writing is easy because this is still, still ArchGDO and ArchGDO geometries. But if I now write this, so this was a shapefile. I write it to a new shapefile, and now we can actually use shapefile.gl, which is a native reader of shapefiles. So let's do that. That's shapefile.table. I get something back. I don't know exactly what it is. Because of course shapefile has a way different interface than what I'm used to. But shapefile itself, just like many things in Julia, they implement the tables interface. So again, I can call DataFrame on that shapefile object. And I'm really not defining all my packages. I clean too much. So DataFrames. Of course, we saw this already, but now the difference is that the geometry column in this data frame is now a polygon with 472 points. So not iGeometry anymore. This is actually type polygon. So if we look at the type, we can expect it further. So polygon, 472 points. So again, this is a shapefile specific geometry of the shapefiles package. Don't know how to handle it. This now has, well, parts and points. Points sound good, but still. But because this also implements GeoInterface, we can again just go over it, request whether it's a geometry, and if so, yes, then we can request the coordinates. And this also doesn't have a CRS. And the fun thing now is that we can actually, this is df2 by the way, we can write it to, again with GeoDataFrames, we can write this table. And this is a different table with a different type of geometry, but GeoDataFrames can write it. Which is very nice, I would say. So basically, if you support GeoInterface in your package, you enable much more functionality in other packages as well. So you make it way easier for the users. And basically, if you provide a GeoInterface like geometry, provide the column, default name, that's why it works without specifying it. But if you would put a question mark in front of GeoDataFrames, you would see that there are option GeoColumns. So we could actually provide it with other options to specify another column in your data frame if you would have named it differently. Of course, this won't work, but maybe your column is named Geom or some other weird name. So in the back, what's happening behind the screens, I've got to say, is that this custom geometry, so this shapefile polygon, is automatically converted to an ArchGDO geometry. So if you want to do that yourself, you can actually call geointerface.convert, just like the base convert, but we call it specifically for GeoInterface. We say I want to convert it to an archdigital geometry, and we give this shapefile thing. And that conversion actually works. So if you implement GeoInterface, you can convert between different geometry representations in the ecosystem. Now it's still a bit hard to actually specify the type of the custom geometry in the other package. But there's now a pull request on GeoInterface. I'm discussing it with Rafael as well, that we can do, I think something like this, archdigital. We basically provide the module as for the conversion, and then this will work as well. So that's up. That's the new feature that will be upcoming. And that concludes the last note I had. So any questions thus far? No, is it all clear? I did see some questions in the chat, or at least there's now 4 more, but I really don't speak Portuguese. So hopefully others can answer whether these were...
It's people complaining about the stream.
Okay, but is that because of me or is it something?
Maybe I didn't read the whole thing.
Okay. Well, I think it will be fine.
No, it's okay, it's okay.
It's okay.
It's internal.
Okay. Then, thank you. I hope to speak to all of you in the coming sessions or lunches and dinners. And again, really feel free, if you hit some bug or something doesn't work, make an issue. Because otherwise it will we're probably here now all together. It's very easy to fix some things. And we can fix it by today or tomorrow. And that will help everyone. Especially because Julia is still young, we really need the users and the users to be vocal. Otherwise it's just the user hitting a bug, be disappointed and leave, and then there will be many other users also disappointed. And I can't even fix it because I don't know about it. Okay, the other question?
Yeah, I have one. Just here on the buffer of geometry.
Yeah.
When you change the 1 degree to 2 to see the size, if you go back to 1 again,
yeah,
it only increases the size. Doesn't go back to the old image. I can show on my computer also.
Yeah, well, it's mutating, right? We overrode the geometry column. So you call the buffer on the buffer geometry.
Okay.
So that's supposed to happen, I guess. Buffer. This one, right?
Yeah.
Yeah, basically we have the geometry column, and we override it.
Okay.
So it's the buffer of the buffer. So it will be
Always.
bigger each time, I expect. Getting uglier each time. Oh yeah, definitely getting uglier. Yeah, so I want to reset it now. Yeah.
Regarding that, this is all in memory, right? So it's not going to change the underlying shapefile.
True, this is all memory. You really have to call write to actually save the shapefile or whatever representation you wanted to disk again.
Okay. But this could depend on the geometry type you're using, right?
No, I'm using ArchGido in the background, and that's not lazy. It will load everything.
Yeah, okay.
Of course, if you have your own geometries, that depends on your geometry implementation.
Yeah.
Although I am aware of mutating raster packages or lazily loading it, but for vector geometries, I haven't really seen that.
Yeah, I mean, the data is much less vector.
True. Okay. Then we're going to help someone with their question or their error. I'm going to stop sharing and well, hope to see you again soon.
Thank you. So after, can we go downstairs to the main room? Yeah.
You had a baseliner. Okay.
Seems to be because I as a title or cross value. Would have some, but the catalog works poorly on the text file. Catalog method in the it's somewhere in the bucket. It's overfitting.
My problem is a critical problem of writing everything, except in fact
Would you like to say, like, investigating further, like what may be happening, right? Like, what's the
Nice, I haven't seen this.
But then why would there be?
But it does sound.
it's the same for every right.
So we made a Archigito update that broke geodata
like
frames.
5-6 classes like that. It's amazing for
In the GeoInterface package, we have the convert method. For a long time, we were half pirating the base.convert method. Then decided that was a bad idea. Also because of the if I really want to go technical, so invalidate all the packages. So we decided to only use GeoInterface convert, and in my latest geodata frames, I fixed that. So it seems that you don't have the latest geodata frames. You need to do package up.
I will show you the status.
Wait, very good. You expect me to know geodata frames versions from the top of my head.
How did you downsample it? Like, how did you?
Something if something is not needed.
Image and each
Well,
because this you can have an area for
Geodata frames
and
know.
there is several pixels that you remove from there.
Yes.
So what I did was
Let me check what's
extract one to downsample was select just one view from this